Hey guys, what's the crack? How are we doing? All ready for that physics tomorrow? How was biology? I'm sure we smashed it. Hi, Aggie. Hey, Serena. Yeah, we'll be doing that at the end because that's a triple topic. Sweaty symbol. Hello. Clara, what's the crack? Hey, Peter. Mac, why scared? Nothing to be scared about. We're going to be pros at the end of this, eh? Biology was easy. Yeah, I heard that. I heard biology was easy, right? But remember, we're going to lock in for physics still. So make sure we got that formula sheet. No, Tony, sorry, it's aimed at higher. It's aimed at higher AQA. The Easter course in it. Hello, Sakina, what's crack? The Easter course was good, so you came back for more, eh? Serena, my day has been grand. Cut a night. It might just be your internet because it seems that everyone else is grand. Leah, am I from America? Yeah, so I'm not from America. Actually, does anyone else guess the accent? Is it foundation, Patel? No, it's aimed at higher, so it is. It's aimed at higher. Praises, you right. Physics is the best science. It's your birthday, Elle. Happy birthday. Yeah, Ireland. Yeah. So, yeah, I'm born and raised in the north of Ireland. So, yeah, that's the accent you hear. But if you can see there that I actually went to university in America. So that's why like some of my words are a little bit American. So I went to MSU, Michigan State University. Does anyone heard of a Michigan State? Know it? Amina, yes, it's aimed at AQA. It's aimed at AQA. So, Miss, do I leave or stay, Miss Samuel? Are you foundation tier? Some of it will be useful, like the first few slides. Most of it, you can decide yourself what's useful or not useful if you're doing foundation tier. You still need to know some of the stuff, but we're probably looking at some just harder questions that you might see on your paper. Is it triple? Yeah, we're going to do combined and triple, combined and separate, Lewis, and then we're just focused on just triple at the end. So yeah, the reason you should listen to me is because when I did my GCSEs, we did A stars then. So I got 7 A stars and 4 A's, and I've been teaching for quite a while. It's physics. Hopefully you know that, Rosie. And I did 4 A stars in maths, biology, chemistry, and physics. So hopefully you guys are all going to want to do physics. So just remember that share this with your friends, right? This is free today. We'll do free hours, and there's so many of you here already, which is so great to see. So if you're happy to be here, just hit that like button. And remember, if you want to type in the chat, so if you can hear me talking to people chat, you need to make sure that you've subscribed. So if you want to type in the chat, you need to be a subscriber mode. So just remember, if you want to share this with your friends, just copy the link and then share it with them. And you can earn money, right? So the more people that you share with, the more money that you guys will get. So it's aimed at AQA, yeah, aimed at AQA. So hopefully this slide answers everyone's question. Yeah, James, the north of Ireland. So yes, we are going to do unit conversions, Sarah. That's what we've got here. County, coloured, you know counties. County Derry. You used to live in Michigan. Yeah. Minty, I went to Michigan State University. Khaled, we're going to review of nearly all of the topics. Yeah, but we're going to do all the topics, just not every like subtopic. So what we're going to do is energy today, electricity today, particle model of matter. Hello, Maria. Particle model of matter and atomic structure. Yes, we're going to go over all of the paper, Olajide, all of the paper. Theo, half Irish, shout out all of the paper. So what we're going to do is the first bit is for combined and triple. All of it is for higher. Boomerang, all of it is aimed at higher. So combined and triple higher. Then we're going to have a quick break. Then we're going to do more combined and triple. Again, all aimed at higher. All of the topics are higher boomerang. And then we're going to have a break. And then the last 30 minutes is for triple only or separate science only. So remember, for triple, you have to know everything that combined has to know. It's just a little bit stuff that are extra at the end. All your physics teachers are Irish. So then there's a QR code there if you want to scan it. So you can see how there's a QR code here for combined and a QR code here for triple. So just make sure that you have your formula sheet, your data sheet. Tahima, hello. Anyone else here from our full course? I see Tahima. I recognize that name. Adam, foundation does need to know everything, but we're aiming at higher. So if you're doing combined, scan this QR code to get your formula sheet. And if you're doing triple, scan this QR code to get your formula sheet. Afia, hello. Here from Easter Revision. Yeah, guys, this is great. So if you're excited that it's free and you're excited to learn something, just hit that like button there so we can just get started. The class, if we get 500 likes before we even start. So we're at 240. I think we get to hit the 500 before we even start, eh? So it's free, which love is remember share it with friends. If you're doing paper one combined, hopefully everyone's aware your exam will be 1 hour 15 minutes. If you're doing paper one triple, hopefully everyone's aware that your exam will be 1 hour 45 and your exam is tomorrow, right? It is aimed again. We're aimed at AQA today. So it's aimed at AQA. And if you want some extra stuff, I've also got a TikTok page. Anyone here see my TikTok page? If you have the TikTok page, this will be really good for you right before your exam tomorrow. So there's loads of TikToks here, just really quick, like 2-minute videos, 3-minute videos, just helping you out on that content that you need to know. Yeah, so on that content you need to know. Guys, 500 likes. Awesome. Okay, so I'm just going to label these A, B, C, D, E, F, G. Yes, I can say my alphabet. So either match the numbers up or right beside them, what are the correct units? So what are the correct units? About 80% of Excel and AQA are the same, yeah. Mel, if your foundation is useful, but it's aimed at higher. Okay, so we're saying A to 5, James A to 5. We're saying 8 to 5. Yeah, beautiful, right? Time has to be measured in seconds, right? The easiest one. If we're given it in minutes, we know that there's going to be 60 seconds inside 1 minute. So if they give us time in minutes, we just have to multiply by 60 always to get it into seconds. Just make sure you're always giving it in seconds. Yeah, Jude, beautiful. B1. So mass is always measured in kilograms. Nice. Everyone is aware that you're in physics, right? That is different from chemistry. So please don't make that mistake. I know you've just done a chemistry exam. Mass has to be in kilograms. So remember, if someone gave me 1K of cash, that means they gave me £1,000, right? Hopefully. So 1 kilogram is 1,000 grams. So remember, you're in physics, it has to be in kilograms. So you need to divide by 1,000 to get it in kilograms. Yeah, this is not in the workbook just because of our intro slides. It's just a way to make sure everyone gets started, gets warmed up, gets active in the chat. So remember, if you want to write in the chat, you've got to be a subscriber. Right? We're saying purple shadow E to 3. So energy is always measured in joules. Beautiful, good job. Kaya, we're saying, was it F to 1 there? You said work done, no, kilograms. Jazz, G to 7. Distance is measured in meters. Beautiful, good job. And sometimes they give it to you in kilometers. So remember, the same thing as 1K of cash is £1,000. 1 kilometer or 1K is 1,000 meters. Yeah, nice. Coconut from Ireland. Woo! Okay, next one we're saying that, what we're saying here, we're saying D to 4 local. So D to 4 force is always measured in newtons. Nice, after Sir Isaac Newton. Please remember that has to be a capital N. The amount of people who use a little n is wrong, okay? If you're triple, can you tell me what a little n stands for? So if you're triple or separate science, you should know that little n stands for. Bella, hello, C to 2. Weight is always measured in newtons. Good job, because weight, remember, is the downward force to gravity. Yeah, Lily, nice. Yeah, Kiera, nice, good job. Remember, little n stands for nano, or nano means times 10 to the power of -9. So that's something you knew of triple. No, Thea, look up here. It's combined and triple. Someone asked what we're doing today. We're doing these 4 topics today. Playthings, moles, you're back in chemistry. Weight, S, why is weight not in kilogram? Because remember what weight is. So maybe this is a good one because I've seen a few people ask it there. Weight is the downward force due to gravity. So because your weight is your downward force on you. So again, if I'm standing on the earth, there is a force pulling me down, and that force is called my weight. Okay, so weight is that downward force due to gravity. So as a force, it has to be in newtons. So be careful, that's one as well that people struggle with. Okay, last one was work done. And work done, yeah, Sham, beautiful, is that we're saying that it's going to be work done is going to be in joules. Yeah, nice. Work done, again, is one that missed out. Olivia Books, hello. Work done, yes, it is, Millie. Work done is one again. A lot of people forget. Work done is always measured in joules. Okay, so that come up. Work done is always measured in joules. Anicia, I see there, what's the difference between weight and mass? Okay, it's kind of more of a paper 2 topic, but there's an equation on paper 2 that says weight is equal to mass times by gravity. So weight is a downward force measured in newtons. Your mass is how much matter is in your body, measured in kilograms. And G is the gravitational force acting you. Yeah, no, good job, which is 9.8 on Earth, but that's more of a paper 2 topic. Tima, we're covering most of them, not all. Okay, so again, just make sure we're good. What is 10 kilojoules into joules? Yes, it is, Stanley, good job. What is kilojoules into joules? Tyler, look up here. It is all higher. It's all aimed at higher. Good job. Lovely, lovely, lovely. Yeah, nice. Good job. Everyone knows that, remember, 1K of cash is £1,000. Yeah, Margaret, nice. So what we know to get 10,000 is going to be 10,000 joules, right? 10K is going to give us 10K of cash. They give us 10,000 joules. Good. What if someone give me 200 grams, right? Because we know we're in physics as being kilograms. Yeah, Cooper, nice. MH, nice. Lily, nice. Moonlight, nice, good. It has to be divided by thousands. Remember, if I know that 1K of cash is £1,000, 1 kilogram, 1K is 1,000 grams. Remember, to get from grams to kilograms, we always divide by 1,000. So again, if I divide by 1,000, I get 0.2 kilograms. Remember, it has to be in kilograms in physics. Yeah. No, Sophie, it has to be in kilograms, always in kilograms. Okay, what is this? 3 little m-a to a. Morpheus Foundation does need to know most of it, but we're going to be looking at some harder questions that won't be asked in higher. Ruby, tell me what's wrong. So what does that little m stand for? Yeah, beautiful, nice, good. Nice, yeah, milliamps, Catherine, nice. So what that stands for is 3 milliamps. Okay, so remember, how I remember this, for I would do it, is a millipede has got 1,000 legs. So 1,000 millimeters inside 1 meter. So if I want to get out of that milli, the math we do there is divide by 1,000. So nice that people spot it. This is 3 milliamps. I want to get it into amps. So to get it into out of that milli, we divide by 1,000 and we get 0.00 divided by 10 divided by 100 by 1,000 amps. What is amps the unit for? Just make sure we're good, because that wasn't on our sheet there. What is amps the unit for? Someone said that was milliamps. Yep, Isla, very, very quick. Good job. Pranav, hello. Good. Current. Nice to see a lot of you from my full course. Yeah, it is measure of current. Okay, current. Good job. Okay, which is larger? This is something that Triple needs to know, and it's starting to come up a lot more in combined. Is 10 gigajoules or 90 megajoules larger? Which one is larger? Bella, beautiful, good job. Giga, remember, means times 10 to the power of 9, and mega is like million, right? So that one is times 10 to the power of 6. So which one's bigger, a gigajoule or a megajoule? Yeah, beautiful, right? Gigajoules is the biggest you can think about. Maybe you remember like megabytes of data or gigabytes of data. So if you have a gigabyte of data, that's a lot more data that you've got than if you have a megabyte of data or a kilobyte of data, right? Yeah, beautiful, good. Yes, Eden, it's aimed at AQ, it's all aimed at AQA. Yeah, Pranav, that's even larger again. Yes, they do S, because it's come up last year. It came up as a multiple choice question asking which one was bigger. So yeah, it's something you need to know now. Yeah. We're at 657 likes. Lovely. Okay, next one. Hey, am I Aussie? No. Aggie, what do you mean when we're starting? We've been going. We've been doing our units. You don't need to know, Tara, no. Okay, first one says kinetic energy. Okay, you have to know kinetic energy is to do with anything that is moving. Sanjid, thank you for the equation. And the equation to calculate kinetic energy is equal to 1/2, Amber, beautiful, 1/2 of the mass times the velocity squared. Salmon, measure. I have no Aussie in there. So hopefully all of you have scanned your formula sheet and you can see there that I can see kinetic energy is 1/2 of the mass times the speed squared, right? It tells you that in your formula sheet that you need to look at tomorrow. Remember, side 1 is going to be all the stuff that is on your paper 1, right? So again, someone just said there, what does M stand for? French toe. If you look at your formula sheet, remember at the last slide there, you should have scanned the QR code to get your formula sheet. And if you look at the formula sheet, look at the very top there, it tells you that kinetic energy is 1/2 of little m, which is mass, times the speed squared. No, Sadia, you don't know any of our formulas off by heart. You just need to look at the ones you're given. So again, we've got a car. So what I'm doing, calculate its kinetic energy, is moving. I do 1/2 times its mass, and my mass is in kilograms, so that's good. Yep, it's AQA, times by its speed squared. So it's speed squared. So to get, Sarah says we're going to get 4900000. So Sarah says we're going to get this number. Do we agree? Live 4900000. You agree? Esme, yes, you do. Yeah, beautiful, good job. And what's my unit? Because remember, we always want to have our unit. Yep, Nirvan, good, joules, right? So if this came up in your exam, that would be a 3-mark question because they didn't give you a unit, okay? And just to make sure everyone was good with the square button, if I had my calculator out, what we're doing here in our calculator is doing 1/2. 1/2, another way you can write it, like we saw on our formula sheet, is 0.5 times the mass, which was 2000, times by the speed, which was 70, and then you just square it. And then that's how we get the answer of 4900000. Please just be very careful that you type in all the zeros, okay? If you hit this button here that says ENG, does everyone see it? If you hit the button here that says ENG, you can switch it into standard form. So you can write either one you want. No, Angel, don't convert into kilojoules. You only put mass in kilograms. So I can write 4.9 times 10 to the power 6. So 4.9 times 10 to the power 6 joules. Both of them will get you full marks. So everyone your calculator says is the one that you use. Okay? Or calculator says is the one that you use. Yeah, look at you with your megajoules. Good job. Johanna, it's aimed at, so this question will be on higher and foundation, but again, we're aimed at higher. You know how you've written it, kind of read it like that, or do you have to write 1/2 mass times velocity squared? No, if you write so in your exam, it might say like state the equation. If you write the equation like this, you will get full marks. But if you write that the energy is 1/2 of a capital M times a capital V squared, you will not get the marks. Okay, so yes, if it asks you for an equation, you can just write the formula, right? Because it's given to you in your data sheet, but you have to be careful to use the right letters. So a capital M, remember, stands for mega. It doesn't stand for mass. So just be careful that you use the correct letters. The equations link back. Ibrahim, yes, I can. So I'll go back quickly. So remember, just scan the QR code. So if you take your phone, just bring it up here, scan the QR code. That will take you to your formula sheet for your exam board, right? So if you're doing combined, remember you're scanning this one. If you're doing triple, you're scanning this one, and it'll bring up your formula sheet for you, okay? Hearts, no, it doesn't have to be in standard form. Remember, all you want to do is that whatever one your calculator says is the one that you write. Okay, so whatever one your calculator says is the one that you write. Kezinet, you can if you want, but I wouldn't recommend. I would just write down what your calculator says. Yeah. Okay, next one. This one we're looking at elastic potential energy. Yeah, Abdul, again, if you look at those formulas, you get all the formulas there that were on that QR code. Yeah. Rashid, we will do some. I said that at the start. Nabila, I'll show you again when we do this example, okay? Use that ENG button on your calculator. Okay, so again, it says a spring has a spring constant of 300 newtons meters, is stretched from 6 to 20 when weights are added. Calculate the energy stored. So hopefully what you're doing right now is you're pulling up your formula sheet, that data sheet. You're looking for equation to calculate energy to do with springs constant. Dark, what's wrong? Yeah, beautiful. Beautiful, guys. Lovely. A lot of us are getting the same answer, which is nice. Yeah, good. Amber, nice. Ikra is saying it's going to be 29,400 joules, which is nice. You wrote joules. S, you don't have to write the equation, but it's good practice. So if everyone sees here, the energy is 1/2 times K times by E squared, right? It tells me it right there. It tells me K is the spring constant. So the energy is 1/2 times by K is 300 times by extension squared. What did you guys use for extension? What did you guys use for extension? Yeah, this is Hooke's law. Nice application. Beautiful, right? So remember what extension means. Good. Yeah, good, guys. What extension means, remember, it means change in length. Yeah, Peter, thank you. It means change in length. So if I look at the change in length here, I'm going to get 14 centimeters. Yeah, good job, Alaya. Good. So why are we supposed to do 0.14 squared? So 14 centimeters. So why are we writing 0.14 squared? Yeah, good. Exactly for that reason, right? We just said in that previous slide, distance has to be in meters, right? It has to be in meters. Good. So the way I remember it is, you know, a century from history? A century is 100 years. So there's 100 centimeters inside 1 meter. Okay. Do not forget that unit conversion. So what we should have done was divide by 100 to get rid of that centi. Okay, so if I divide this number by 100, maybe you want to use our calculator to double check it. So again, if I use my calculator to double check it, you would have done 14 divided by 100 equals 0.14. Now what we're doing is 0.14 squared, so the square button. We're then multiplying it by 300, and then we're multiplying by half, or the same thing as a half is 0.5, like it says in your formula sheet. So then hit that S to D button to get rid of that fraction, and you should get 2.94. Yeah, good, guys. So does everyone see what the problem was there? 2.94 joules. So, sorry. That would have been a 4-mark question. If you got the answer that a few people said at the start, how many marks would that be? How many marks would you got if you wrote 29400? And it goes to 830. Yeah, good, guys, right? This would have been 3 marks, okay? Because what they forgot to do was they forgot about their unit conversion. So please, loads of you, if you go back in your chat, loads of you wrote this answer. And think how many of people then would have lost that 1 mark, okay? So be careful there. Remember, do not forget about your unit conversions. We said at the very start, distance has to be in meters. So you have to convert it into centimeters. You have to convert it out of the centimeters into meters. Yes, SA, all higher and foundation needs to know this. And everyone asked there, what time do we end? We're ending at 8 p.m. today if you're doing combined. We're ending 8:30 today if you're doing triple. JJ, exactly right. Yeah, that 1 mark does make the difference. That 1 mark can make you a difference in the grade boundary. Yeah, nice. Okay, cube core, beautiful, good. The next question then is, what is the resolution of our ruler? So what is the resolution of a ruler? Yes, you would, KADZ. What's the resolution of a ruler? Oh, it's not 1 centimeter. So why is it's not 1 centimeter? Remember what resolution means? It means the lowest. Good job, Red Shadow. Good job, Fahim. It's actually 0.1 centimeters. Yep, good, nice, Harvey. Or you can write 1 millimeters. Good job. So what resolution means? It's the lowest number that your equipment shows. So the lowest number that your equipment shows. So all of you should have a ruler in your exam tomorrow, and you see the lowest number in your equipment. Yeah, DX, beautiful. The lowest number in your equipment, Annie, what do you mean ruler? Like a ruler that you'll have in your exam? Do you know a ruler? Like, am I saying it weird? I don't know. A ruler, right? You know, there's like 1 centimeter, 2 centimeters, 3 centimeters, and they've got all those like tiny little lines beneath it. Mohammed, what does Laura call it? Oh, Mohammed, that technically is a definition, but you never get asked for the definition. I would say that doesn't really help you figure out what it is. You're just looking for the lowest number on the equipment shown. So technically, if these were measured with a ruler, what should they have written? Can anyone fix this? If these were measured with a ruler, what should they have recorded in their experiment? Lucas Jones, I agree. Yeah, we don't know what a ruler is. Not sure we're ready for this exam tomorrow. Okay, so what? Thank you, Katie. Good job. Afia, good job. Nice. They should have wrote 6.0 centimeters. They should have wrote 20.0 centimeters. Everyone good with that? Because they used a ruler. Remember, a ruler has the lowest resolution of 0.1 centimeters or 1 millimeter. Again, someone says, don't know what resolution is. Again, I just said it's the lowest number on your equipment. So if you're looking at your ruler right now, all of us should be very aware that the lowest number there is a millimeter. Okay, I'm a little bit worried if you don't know that that's a millimeter. Yeah. So the smallest number on your ruler is a millimeter. Okay, next one. A potato head falls to the ground, losing 0.049 joules of gravitational potential energy. It fell 60 centimeters. This was a past paper question. It tells you what number to use for gravitational field strength, and it says give your answer to two significant figures. So what we write in, I'm saying 0.0084, I'm saying 0.081, I'm saying 0.0 says 0.084, I'm saying 0.083, Riri. Lily, mighty God in heaven, Pranav, yeah. Sheba, I am Irish. Yeah, I'm from the north of Ireland. So anyone from Korean? I'm from Korean. And again, if you've just joined us, remember, if you want to type in the chat, you just need to go, you can only chat if you're a subscriber. Just remember to like and subscribe. We've got 800 likes right now. So remember, if you're loving that you're learning something for free, like it. No, we're not doing calculations the whole time. We're starting with energy and then we're building up. So it's going to get more difficult as we go along. Yeah. Aliyah, thank you. Good job. First thing we should have noticed was this unit before we do anything else. Centimeters, right? Remember, a century is 100 years. So there's 100 centimeters inside 1 meter. So to get out of centimeters, remember, we divide by 100. So if I divide 60 by 100 in my calculator, I get 0.6 meters, right? So hopefully everyone didn't forget about their unit conversions, right? Unit conversions. Okay, so what I can see here, it says gravitational potential energy. So what I do is I pull up my formula sheet. Yes, we're doing electricity. If I pull up my formula sheet, I look for something that says gravitational potential energy, and I see that equation there, the third one down. So we know to calculate the gravitational potential energy, we do mass times gravitational field strength times by the height. Right? Mass times gravitational field strength times by the height. You hate unit conversions. S, you're going to be a pro at them by the end of this, I'll tell you that. They're going to talk about units the whole way through your paper tomorrow, okay? Please look out for those units. Yelena, it has to be in meters because like we said at the very start, remember we did that matching exercise, we matched them up. Distance has to be in meters, has to be in meters. Yes, Thea, like we said before, if you didn't convert, you would have got 3 marks instead of 4. So to calculate the energy, but don't lose them. The mass, we don't know, doesn't say anything about mass. It says G, I'm going to use 9.8. And the height, we do know, was 0.6. Okay, so this time they gave me the energy. Lori, we're going to do a bit of that in a second. So this time they gave me the energy. So I know that 0.049 equals M times 9.8 times by 0.6. Salmon, yes, we're all getting 9s. I like that positivity. Yes, we're going to have circuits. So what I would do first is I would simplify that, right? So I would multiply these two numbers together first to get rid of it. So what we're going to do is that we're going to do 9.8 multiplied by 0.6 in order to get rid of that part, which is 5.88, right? So what I've got here is mass times by 5.88. Hopefully everyone finds this easy and we're thinking, how do we calculate mass? We know do the opposite of multiply is divide. So instead of multiply by 5.8, we do the opposite of multiply, which is divide. And what we do to one side, we do to the other, right? That's how we work it in maths. Note, we're starting with maths. We're starting with equations because 70% of your exam tomorrow is going to be equations. And then we're also going to cover electricity, specific heat capacity. We're covering all of the topics. So 0.049 divided by 5.88. And what we're saying is our answer. I'm saying 0.12 kilograms. I'm saying 5.9, 0.0083 from ocean. Why do we divide now, Talia? Because the opposite of multiplying is divide. And what you do to one side, do the other. Yeah, beautiful. Guys, 0.0083. Some nicey people got that. So 0.0083. If you wrote 84, you're wrong, okay? So many of you wrote 84, that is wrong, okay? So I had a little dot there. So if some of you are stressed what that is, that's recurring. So 0.00833333333, right? Never ending. So what you need to do is you look at the next number. If it's below 5, you leave it alone. Ria, is it grams or kilograms? You tell me. What is mass always measured in? MH, yeah. 70% of your exam is maths. You bet, Patia, we're going to get to it. Yeah, beautiful. Mass is always in kilograms. Your final answer should be 0.0083 kilograms. Mass is always measured in kilograms. No, Thea, we don't round up because that number is less than 5. If the number is less than 5, you always round down or just leave it alone, basically. MJ, that's what it says in my calculator, but in my final answer, no. So in your final answer, you can never have fractions in physics and never have recurring decimals. Okay, so never have fractions, never have recurring decimals. Yes, they will also accept, so that's perfect, they will also accept standard form. So if you wrote 8.3 times 10 to the power of negative 123, the negative 3 kilograms, that is also full marks. Just no fractions, no recurring decimals. P.S. I've answered you twice. Yes, we're doing content and calculations. Okay, next one. So this one is the law of conservation of energy. So it says energy cannot be created or destroyed, only transferred. So it says a stone of mass 50 grams, hopefully you're thinking warning, is catapulted into the air and reaches a height of 20 meters before it descends and hits the ground. Use G is 9.8. How much GPE did it gain? Yasmin says 9.8 joules. 9.8 joules is Maka. 9.8 joules. Bella, 9.8 joules. Ella, yeah, most of your physics paper is maths. That's why we focus on joules a lot. Johanna, please be careful. And I see if 3 people have written it now. That little j is going to get you no marks. Okay, joules has to be a capital J. Yeah. Head, if I get the answer all right and show equation and sub to in but forgot to show arranging, if your final answer is correct, you always get full marks. Just don't do that just in case you do something wrong. So hopefully everyone saw we look for gravitational potential energy in my sheet and I see mgh. So the mass, I'm thinking has to be in kilograms, right? We're in physics. Yeah, beautiful, Amelia. Thank you. So remember 1k of cash is someone give me £1,000. So if I have 1 kilogram, I know that's 1,000 grams. So remember to get into K, we divide by 1,000. So what you should have done here was divide this number by 1,000 to get 0. Divide by 10, divide by 100, divide by 1,000, 0.5. Goat, again, we're doing theory right now. You might think this is just maths, but it's not theory. You need to understand that energy cannot be created or destroyed. Cece, of course, happy birthday. Yeah, you don't get marked for using the right equation. You get marked for putting the numbers in the right place. And thank you for people paying attention today. It isn't 0.5. Yes, lovely. I'm just checking that everyone's good. You would lose a mark if you did that. It's 0.05, right? And if you're stressing about that, what you need to do is that you're popping it in your calculator to be sure. So 50 divided by 1,000. So thank you for those paying attention is 0.05. Okay. So remember, just trying to show you can lose marks for that stuff. So use your calculator if you need it. G is 9.8 and the height is 20. So all we do is we pop the numbers into your calculator. Maybe just turn your volume up. So we times by 9.8 and we times by 20. And I get a number. Again, we can't have fractions in physics. So it's going to be 9.8 that people got ages ago. So Aisha, good. 9.8 capital joules. No, we don't convert meters when we said at the start. Some of you might need to go back to that first slide. Again, I'm a little bit worried if right now we haven't learned that distance in meters, right? So please go back to that first slide where we've matched up distance across to meters. Okay, distance has to be in meters. Yes, we're good. Okay, calculate the speed of the stone just before it hits the ground. So some people want it theory. Tell me the theory. How do we calculate the speed? Rahia, the same way I did here. Think about things you know about. 1k of cash is £1,000. So Bella says it's going to be 19.8 meters per second. I usually trust Bella, so I'm going to say she's right. What do you think? Nope, I can't calculate the speed by doing distance divided by time. Nope, we don't do that. Energy is conserved, Raya. Good. So what does that mean? So think I've got a stone that has been thrown up and it's going to fall back down. We calculated that the gravitational potential energy up here was 9.8 joules. And I want to calculate the speed just before it hits the ground. So what is that energy transfer? Yeah, beautiful, guys. Good job. We just said energy can't be created or destroyed, only transferred. Nice. So all of this gravitational potential energy, because it's height above the Earth, as it falls down to the Earth, that gravitational potential energy decreases, 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 because the kinetic energy increases, 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 because as it falls, it speeds up. Yeah, Minty, good. So what we're saying is all of our gravitational potential energy is going to go into our kinetic energy. So nice you figured that out. So the kinetic energy we know then is going to be 9.8 joules, right? Energy is transferred, right? Energy is changed from one form to the other. So now I know the kinetic energy. I know to use kinetic energy, I know is 1/2 of the mass times the speed squared. Yeah, said Kia, good. Martha will talk about that in 2 seconds. Actually, Martha, it's a good question. Martha says once it hits the ground, where did the energy all go? Atoms for everybody. If you get the wrong unit, you lose a mark, Cram. Cube core says 19.82, so does ocean. So again, what we're doing is 9.8 is equal to 1/2 of the mass. Please remember our mass is 0.05. Do not use 50 because it has to be in kilograms times our speed squared. This one's a little bit harder. So what I would do first is do 1/2 of that 0.05 to get rid of it. So yeah, energy is dissipated. Lovely. That's a nice answer. So what we're doing is 0.05 divided by 2 because we're trying to simplify 0.025. So what I have now is 0.025, Tahima, beautiful, times by v squared. A lot of us are saying when it hit the ground, the energy gets transferred or dissipated into the surroundings as thermal. Okay. So now I think, how do I get v squared by itself? To get v squared by itself, we do the opposite of multiplying, which is divide. So what I have to do is I need to divide both sides by 0.025. So we do 9.8 divided by 0.025, and we get a number there of 392. Okay, so many people leave it here. Why am I not finished? Why are we not finished? Sarah, we're using kinetic energy. So here, remember we said all of that gravitational potential energy gets converted into kinetic energy. Because remember we said before, kinetic is anything that is moving. And we said here about a speed. Yes, beautiful guys, good. That is v squared. The question wants v, it wants the speed. Yeah, beautiful, nice, perfect. So what we need to do is we need to square root our answer. So take the square root of my answer, and I'm going to get 14 root 2, but again, I'm going to press my S to D button to get that into my fractions, and I get 19.798. So what's our final answer? Tiana, yes, beautiful. We're going to write 19.7 is wrong. 19.7 is wrong. 19.798 is wrong. 19.8, beautiful. Yes, it has to be, the only acceptable answer there is 19.8, and speed is always measured. Yeah, good. Yeah, we got it. Yazin, good. Meters per second. Speed is always measured in meters per second. Meters per second. The sister is beautiful. EK, that's our kinetic energy. Remember we said that when something is really high above the surface of the earth, it has loads of gravitational potential energy. And as it falls, it loses that gravitational potential energy and it gets transferred into kinetic energy, right? Because it speeds up. How do I know when to round it? Because if I look at my calculator, you can, if I look at the numbers there, I've got 19.79. I can't write 19.79 because the 8 is above 5. It makes it round out. I can't write 19.798 because the 9 after is above 5. It'll make it round up. But you could write 19.799. So you could have written 19.799 meters per second. That's the only other option because 19.7 is wrong. 19.78 is wrong. Could you write 20? No. I wouldn't write 20 because you're rounding too much. Yeah, you're rounding too much. Oh. Sorry, that's my dog. Didn't you just hear? I think he hears the postman. I'm trying to shout at him, but every time I shout, I'm trying to put the on mute. No, if you're doing triple or combined, you shouldn't be using formula triangles, not in higher. Formula triangles you shouldn't be using if you're doing higher, yeah. So we're gonna just not focus on form. We're aiming at higher. Dog, the dog give you a heart attack. Yeah, he's a German Shepherd. Do you guys know German Shepherds? He's an angry dog. He is. How many marks? For the first part, if you got 9.8 joules, you would have got 3 marks. And for the last part, if you would have figured out that the energy is transferred, there's your 4th mark. 5th mark is for writing this line out perfectly. The 6th mark would have been your number. So this one would have been like a total of 7 marks, maybe 8 if they're being kind to you. Yeah, maybe 8 if they're being kind to you. You want to see the dog? I'll show you the dog in the break. How about that? If we can get our likes up to 2,000, then I'll show you my dog. I'll let him have some time to spotlight. We're gonna get our like. We're at 997. Okay, next one. Law of conservation of energy. What is it? Write your answer in the chat. We need to know this. What is the law of conservation of energy? At Anis, we have to. The triangle is more like if you're not very good at your maths. But hopefully all of you want to do physics for A levels. So no, you shouldn't be using triangles in your A level physics. Energy cannot be created or destroyed is not finished. So energy cannot be created or destroyed, sadly, is not your marks. Yeah, only transferred. Yazin, perfect. Purple star, perfect. Yeah, good. Right? Law of conservation of energy is energy cannot be created or destroyed. Only, and please don't forget that, only transferred or only changed from one form into another. Yeah, Gabby, perfect. Only transferred. Yeah. 1.2k likes. You guys are desperate to see the dog, eh? Okay, let's do our energy transfers now. We're going to do fission and fusion at the end. That's only triple people have know about that, not combined. You can use the triangle method. So if you really like the triangles, you can use them. Butterfly, if you really like the triangles, you can use them. They're marked as long as you get the right answer. So if you want, I can try to do some triangles now as well. David, beautiful. Yes. Okay. So kinetic energy, if we throw a ball up, right? If I throw a ball up in the air, I know as it goes up, it's gaining gravitational potential energy. So that's why all of my kinetic energy is going into my gravitational potential energy. Perfect. Good job. So remember, if you throw a ball up, when you first let go of it, it's going super fast. That's why it's got loads of kinetic energy. And as the ball goes up, it decreases in speed. And then what happens is it's going to increase in speed as it goes down. Yeah, nice. So what about a man running? Chemical energy goes to what? Gabby, good job. You've got us there, eh? Imogen, beautiful. Nice, nice. Good job, guys. Yeah, perfect. My dog is called, you get my dog's name at the 2,000 likes. Okay, chemical energy is going into the kinetic energy. Bribery. Okay, so a man has chemical energy and it's going to kinetic energy. Remember, kinetic is things moving. What is chemical energy? Because a lot of people miss that. Why does the man have chemical energy? Where did he get his chemical energy from? Bella. Yeah. Aisha, yeah. Where did he get his chemical energy from? Yeah, thank you, good. He got it from his food, okay? So that's why if you think about a marathon runner, that's why I think about you tomorrow for your exam. Do not go into your exam if you haven't eaten. Because you haven't eaten, your brain is a muscle, right? Your brain is an organ. If you don't put food in your body, your muscles don't work the same, okay? You need to have chemical energy so that you can move, so that you can think, okay? So again, chemical energy, remember, is found in your food and your fuel. Specific heat capacity is next. Okay, what about a wood in a fire? So what energy did the wood have to begin with? It's really simple. I love food. Beautiful, Neuron, sorry. Yeah, good. It's chemical. Because wood is a type of fuel. So my chemical energy is our food and our fuel. When we burn the wood, it turns into that thermal energy. Remember, thermal energy is anything that is hot. Newton's laws behind preheat is on paper 2. Okay, this one's stumps a few people. What about a car stopping? Is it aimed at AQA? Oh, Pranav, perfect. Good job. Riley, perfect. Good job. Oh, a lot of us got this. Yeah, very good. So if we got a car stopping, it must have been moving to begin with, right? So it must have had loads of kinetic energy because it was moving to begin with. And if you think about a car that stops, if it was going really fast and it stops, think about those sports cars. If anyone's interested in Formula One, you might see all that smoke around the tires. And all that smoke around the tires, that is our thermal energy. So that's where it goes. It goes into thermal energy. It gets dissipated or transferred to the surroundings. Salmon, it's aimed at AQA. Okay, next one. A roller coaster falling from the maximum height to the bottom. Alia, normally when something, if you don't know what the energy is, normally the answer is thermal. Sanjeev, perfect, good job. Nice, nice guys. Yeah, easy, good. Right, think about a roller coaster. If I'm on a roller coaster and I'm really high above the surface of the earth, I know what that means is I have loads of gravitational potential energy. And as we go down, we're going to speed up, speed up, speed up. So that's why we go to our kinetic energy. So as we fall, the gravitational potential energy decreases because it all goes into that kinetic energy. Yeah, it all goes into kinetic energy. Few people talking about Formula One there. I referenced it. Formula One, I have a friend who is a Formula One engineer because he studied physics at university. So yeah, it's a really cool career because if you do Formula One, you need to know if it's raining, what type of tires to put on it, if it's windy, how much they should take the turns and the bends. So yeah, it's quite a cool career if you're interested in you like physics. Yeah. Yeah, I would agree. Paper one's easy. Okay, efficiency. What are we going to say? What is my efficiency? It says an electric motor uses 400 watts. It uses lift of 50 kilograms at 0.3 meters per second. What is the work done in 10 seconds? It's aimed at higher. Elif at the very end, maybe thermal energy, but if he's currently moving, he's got kinetic. George, you do get an equation sheet. So if you hear at the start, remember we had that link to get your equation sheet. So it's there for you. So I'll just pop up for this question. Remember, if you just joined us, if you want to type in the chat, you need to be a subscriber, right? So how do we calculate work done? So if you don't see it on the first side of your formula sheet, maybe you're thinking about the second side of the formula sheet, but it says electric motor uses 400 watts to lift 50 kilograms at 0.3 meters per second. What is the work done? Okay, so some people think work done is equal to force times distance. I don't have a force, I don't have a distance. Yes, beautiful, nice. People are thinking work stands for energy. Remember we said at the very start, work is measured in energy in joules. Beautiful, because we don't have a force and distance, so we can't use that equation. Nice. So I'm thinking it's an energy in joules. So what work are we doing if we lift something up? What equation are we using there? What work are we doing if we lift something up? What type of energy? Yeah, good job. Energy over time is power. Good job. If I lift something up, yeah, thank you, Riri. What we're doing is gravitational potential energy. Yeah, Bella, beautiful, ever good. Right, we're lifting it up. So we're using that gravitational potential energy, which is M times G times H. That's my gravitational potential energy. Okay, if I'm lifting 50 kilograms at a speed though, because look, I wasn't given a height anywhere. So what other type of energy are we thinking if we're lifting it up? So that's 50 kilograms at a speed of 0.3. Yeah, thank you, kinetic, right? So do you see what we're trying to do here? First thing you thought, work done. You thought work done is force times distance, but I didn't have a force anywhere, so it can't be that equation. Then I thought if I'm lifting it up, oops, sorry. Then I thought if I'm lifting it up, that it'd be gravitational potential energy, but I don't have a height anywhere. So that's why now I'm thinking kinetic energy. So kinetic energy, MH, lovely, is a jump scare, 1/2 of mv squared. We're going to get to that immediately in a second. So yeah, nice everyone said that another equation we have there is because I have a power, I know power is equal to an energy divided by time. You're 100% right. So what we're thinking here is 400 watts as a power is an energy divided by time in 10 seconds. So to calculate the energy, what do? The opposite of divide by 10 is that we're going to multiply both sides by 10. So that's why everyone's got an answer there of 4,000 joules. But the question wants the efficiency. So do you see how that's not enough? Because if I look at my formula sheet, and if you look at the other side or the first side there, we can see efficiency is the useful energy over the input energy, right? So what is our useful energy here? Good job. That's when we think about our kinetic energy. So that's why we had to think there must be another type of energy here because I only have one number. I need to calculate the efficiency. So we need to have two energies. So what I'm going to do here is 1/2 times the mass times the speed squared. So in our calculators now, what we're doing is 1/2, which is 0.5, times by the mass, which is 50, times by the speed, which was 0.3 squared. And again, energy there of 2.25 joules. Yeah, lovely, guys. Good. 2.25 joules. 2.25 joules. Okay. What are you thinking? How do we calculate the efficiency then? Yeah, Debola. Good. Yeah, LaJoy does chemistry, is my coworker. Power is work done over time is what we did here. So yeah, another way you can write that is power equals work done divided by time. So yeah, what we did was we calculated the work done. We calculated the work done was 4,000 joules, right? But what I want to know was what was the efficiency? So what was the efficiency? So that's why the only way for us to calculate efficiency. So yeah, everyone's right. This is my work done. But what I want to do is calculate the efficiency. So this one we thought about because it said we were lifting something up. So M times G times H, but we weren't given anything about the height that was lifted. So we realized we can't use that formula. So the useful energy here is that the kinetic energy. No, the calculate the work done by the motor. So electric motor uses 400 watts is the power that the motor is using. So we're doing the work done by the power. So that's what our input energy is, right? That's the work done, but it's not all useful. The useful is what we want it to do. So what we want it to do is that we're trying to move it with that kinetic energy. Yeah, good. So then efficiency is going to be super low. Yeah, it's going to be 2.25 divided by the 4,000. It's going to be super low. So super low. So the useful is the thing that you want it to do. So what you do is 2.25 divided by 4,000. And we're getting a number there of 5.625 times 10 to the negative 4. So it's a terrible, right? It's a bad one. It's a bad one, right? It's absolutely terrible. We wouldn't use this, right? It's a terrible motor. So again, what we said was to calculate the work done, we saw that power is work done divided by time, or energy divided by time. We knew the power. We want to calculate that work done or that energy divided by time. So we multiply both sides by 10 to get rid of it. That's 4,000 is my energy. But that's my input. So we're trying to think, well, what's the efficiency? So we need to know what's the other energy. And we can see, Jason, we're doing now, we can see that kinetic energy, something that is moving. So we see that it's moving. Yeah. Yeah, so it's not very efficient. It's terrible. Yeah, it's not efficient. It's terrible. How many marks? You're talking 3, 4, 5, 6, 7, 8 marks. Decimal or percentage is fine. Yeah, decimal or percentage is fine. Okay, some people were desperate for a required practical, right? We were dying for some required practicals here. So here are some practicals. It says a student is investigating the specific heat capacity of a metal block using a heater, a thermometer, and a joule meter. What is meant by specific heat capacity, and state the equation used to calculate it? Cube core, specific heat capacity is the amount of energy required to raise the temperature of a substance by 1 degree Celsius. Cube core, actually that's wrong because you've forgotten something that's really important in your definition. What else is saying? Specific heat capacity, Abdul, is the amount of energy needed to raise 1 kilogram of substance by 1 degrees. Abdul, beautiful. Yes, I like that. Specific heat capacity, what else were we saying? Margaret is the amount of energy required to change temperature of 1 kilogram of substance by 1 degrees. Beautiful. Just some of our spelling is as bad as mine. Lux, energy required to raise 1 kilogram of substance by 1 degree Celsius. Beautiful. Yep, cube core, nice fix. Specific heat capacity is the amount of energy required to raise 1 kilogram. Bella, perfect. Required increase 1 kilogram by 1 degrees. Makala, perfect. Yes, we've all got it. Good. So specific heat capacity, what we're saying is the amount of energy to raise 1 kilogram of substance by 1 degree. Fahim, your spelling probably looks the best there, so I'm going to pin it so everyone can see it. So specific heat capacity, if I was to look at the formula sheet, right? So if we look at our formula sheet, we can see that I've got a specific heat capacity equation there that says that the energy is equal to MC times that change in temperature. So if I want to write what specific heat capacity is, Specific heat capacity is the energy divided by the mass times the change in temperature. Okay, some of you are talking about formula triangles. So if I want to put it into a formula triangle, if they're beside each other in the equation, they stay beside each other inside the triangle. So energy goes on top. So I want to write what specific heat capacity is. I cover the energy. I can say I cover the specific heat capacity. I've got an energy on top and a mass and a change in temperature in the bottom. So that's why I have to say in a definition, we need the word energy. So that's why our definition then is going to be that it is the energy required. Like Fahim said, the energy required to raise, and then I've got a mass in there. So 1 kilogram of substance. And I've got a change in temperature there by 1 degrees Celsius. Okay, so please don't forget that. Don't forget that. Hydrogen 1 goes to the top. If they're beside each other in the equation, they stay beside each other in the triangle. Then the leftover one will go on top. Yeah. Lucy, 100%. If you can do all the maths, yeah, you'll get all the marks. Yeah. Tahima, no, I would not use formula triangles. I'm just putting there because people ask for it. If you know how to do it without formula triangles, just you keep going the way we do it in classes. Okay, how do we do a method to find the specific heat capacity of this block? Am I going to remember? Please write in bullet points. Do not write an essay. Yeah, foundation and higher need to know this. Study account, we'll talk about that in 2 seconds. So study accounts asking why do we put water in that hole? Normally it's not water you use. Can anyone else help out actually answer that question? It's normally not water that we use. We're going to talk about specific latent heat in a second if you want. So weigh the block using scales, measure the initial temperature using a thermometer, turn on the heater, record 10 minutes using a stopwatch, read the energy from the joule meter, record the final temperature, find the difference in energy. Bella, nearly perfect. You just forgot to say what to do with that final and that initial temperature. Is it okay to write both the equation and formula triangle, then use the triangle, show them what you call? You can use a triangle. I just would say that if you're trying to do physics for A level, you probably shouldn't. Yeah. Yeah, you should use oil. Yeah, oil is the better choice. Use a joule meter to measure the energy needed. Smithy, use a weighing scale to measure the mass of the substance. Use thermometer to measure the highest and the lowest temperatures. Good. And then what do you do with the highest and the lowest temperatures? That's what we need to know. Measure and find temperatures. Read the energy from the joule meter. Find the file and record the final temperature. Find the difference in temperature. Yeah, Bella, that's a good one now. Yeah, perfect. It's probably the best one I've seen so far. Place the beaker on a balance and press 0. Why do you have a beaker? Add the water to the beaker and record the balance. Why are you using water? We're using a block. Are you talking about if it asks for a liquid instead of a solid? Ed Space Manager? No, please write in bullet points. Do it in bullet points. Please do not write a full essay. Okay, the amount of times I've marked people's answers and they write this big essay and you end up writing all this information and basically you just ignore those first 2 lines, right? Just bullet point it, write a fact per answer, right? Just bullet point it and write a fact per answer. So what we're saying here, if I want to find the specific heat capacity of my block, we just said mass is in that equation. So how are we going to find the mass? And you tell them how to do it. So we're going to say find the mass using a scale. So nice that everyone said a scale or a measuring scale, right? That's what we need to do. So we've got the mass because I've used a scale, okay? What I need to do is that I'm going to record that delta symbol. Remember that stands for the change in temperature. Okay, so what does change in temperature mean? How many times do we have to record the temperature? Okay, yeah, OCR and Excel need this too. Yes, Rashid, you can say balance. So because it says temperature change, yeah, minute good. I need to record it twice. I need to record the temperature at the start and at the end, right? I need to record the initial and the final temperature. Good. So we're going to say is record the initial temperature. And then is that enough in physics? What you got to say? Am I finished there? Use the initial temperature. Hopefully not finished there. We're saying how? Using what? Yeah, thank you, RHY. Using the thermometer. Yep, Rashid, good. Remember in physics, you have to name the equipment. So please, in physics, name the equipment. Then what we're doing is we're going to turn the heater on. for, let's say what Bella said, she said 10 minutes. You can say whatever you want, whatever time you want. And then we're going to record is the final temperature. So record the final temperature using, again, we tell them what to use, the thermometer. And then how do I get the energy? Because now I've got the change in temperature. Where do we get the energy from? Does anyone know what you call this? You don't have to know it, but good if you do. So then we're going to record the energy supplied. Yeah, Bella, Rashid, good. Record the energy supplied using or on the joule meter. So it's called a joule meter. Normally, though, they will label that for you. So normally they'll label it as the joule meter. So normally they'll label it, but it did say up here that you had a joule meter. So that's where you should have known that word from. So normally do label it, but you should have seen it there in the equation. So finished. People have wrote loads of good stuff on the questions, right? So we said, I've got a heater here. Okay, so remember what we've got is this block, and inside the block, I've got a hole. And in that hole, I place the heater, right? Loads of people ask, and it's really good you're asking this. There's my heater. I need that heat to go into my block. Why do you think something that we do is that we fill it with oil? Why do you think something we do is we fill this gap with oil? So that's a gap there of air. Why might I fill it with oil instead? Yeah, you could do water, but oil's better. Yeah, right? Because that air is an insulator, right? That air is an insulator. The oil is going to allow the heat to conduct. So I want the heat to conduct. I want that connection to be solid. I want the heat to go from the heater straight into my block. Yeah, nice. So nice of you said, fill the gap around the heater with oil. Okay, nice people notice the insulation. Why do we have to wrap it in insulation? So again, I want that heat to get into my block. Yeah, Zara, good. Rahini, we're going to come to that one in a second. Yeah, good job, right? I want all this heat to go in my block. I don't want the heat to go into the surroundings. So what we do is that we wrap it in this insulation. We wrap it in insulation, like if you wrap yourself in a coat to stop your heat getting lost to the surroundings, we wrap it in insulation because we want to reduce the heat loss to the surroundings. Okay, I've seen a lot of people say, why don't you do it the way that biology and chemistry does it, right? I totally get it that in biology you do what's the independent variable, what's the control variable, what's the dependent variable. In physics, you can do that fine, that's grand, but it's much quicker to get marks if you always just state what the equipment is and how to use it. State the equipment and how to use. Do not waste time like biology. So, you know, like in biology, when you do that practical with the little test tubes and you have the potato thing inside it and you fill them solutions and you write that fill the test tubes with equal volume solutions. Make sure you cut your potato to equal surface areas. Make sure you dry your potato. You don't write all that in your physics exam, okay? You literally say, it's already been connected. The picture is here. It is all connected for you, okay? You're just telling them how to use the equipment, okay? So how to use the equipment. Things we could use for insulation is you could wrap it in paper towels, you could wrap it in cotton wool, you could wrap it in anything you want, basically. So Sienna, we found the specific heat capacity because I've got the energy from the joule meter. So I got the energy from the joule meter. I have the mass from my scale, and I have the change in temperature because I found the initial temperature and I found the final temperature. And then I probably should have added a line to find the change in temperature. I should have done the final temperature minus the initial temperature. So I've got the energy, I've got the mass, I've got the change temperature. I just plug them into the calculation to calculate what the specific heat capacity is. Yeah, good. Right, next one. Someone asked about could we do it with a voltmeter and an ammeter? So it says, instead of using a joule meter, another student uses a power pack, an ammeter, and a voltmeter. Calculate the specific heat capacity of the aluminium block if the heater is connected to a circuit for 1 minute. Hopefully you're thinking, warning. The voltmeter reads 6 volts and the ammeter reads 0.4 amps. Okay, this one here, you're talking about maybe a 7 marker. Okay. My favorite topic in physics, radiation. Okay, Leggy B says the final is going to, Jessica, thank you, good. So what I'm thinking, anytime I've got a voltmeter and an ammeter, again, I look at my formula sheet to see how can we use those numbers. Okay, so again, what we're trying to do here is we're trying to figure out what the specific heat capacity is. So I can see my equation for specific heat capacity is MC, change in temperature. So someone said it's only 6 marks in GCSE. I haven't got you an answer line. So normally you'll have an answer line with the unit on it. Because I didn't give you the unit, that's why it's a 7 marker. Okay. So I want to find the specific heat capacity. So we must have the energy, but I don't see energy anywhere. I must have the mass. Do we have the mass? What is the mass? Joseph, I just said there that this would be 7 marks because I didn't give you an answer line with the unit on it. So that's why it's, yes, it would be a 6 marker if I gave you an answer line with unit. I'm okay with that? Audrey, lovely. Fahim, lovely. None, keep talking. Good. So remember, we're not in chemistry, we're in physics. Mass has to be in kilograms, right? It has to be in kilograms. So remember, 1K of cash is 1,000 pounds. So to get out of K, okay, or to get into K, what we do is that we divide by 1,000. So when you divide by 1,000, I know the mass is 1.2 kilograms. Beautiful. Okay, what we're using for the change in temperature, hopefully everyone sees, the change in temperature is 10. So I'm trying to figure out what the specific heat capacity is. So there must be some other way for me to get the energy. So how are we doing here? How are we getting the energy? Anil, beautiful. To calculate energy, if I look at my formula sheet, I can see energy there, or if I look at this equation, I can see power is equal to the energy divided by the time. Okay, so power is equal to energy divided by the time. So I'm trying to figure out what is the energy, right? So there must be some way to get the power because I have the time. What's the time, everybody? So again, power is equal to energy divided by the time. What was the time? Morpheus is triple and combined. Yeah, lovely. 60 seconds. Beautiful, guys. Yeah, Stacey, lovely. It's 1 minute. Remember, that's a unit conversion. We have to have time in seconds. We said at the very start. Yeah, 60 seconds. Nice. Okay, so how then do we have the power? So now you're thinking, I'm even more confused. I don't even have the power. So what are we looking for back in our equation? Why do we have these numbers? How do we calculate power? Yeah, Minati, good. Lovely. I can see a current and a voltage. I know power equals current times potential difference. So the power is my current times by my potential difference. Yeah, beautiful. Good. Am I saying power weird? So yeah, what we're going to get there is 2.4. Yeah, Mizia, thank you. Watts. Nice. Good. So now I know that's my power. So now I have 2.4 is equal to the energy divided by 60. So how do I get the energy by itself? What's the opposite of dividing by 60? What's the opposite of dividing by 60? Nice, good, good. The opposite of dividing is multiplying. So we do to one side, we do the other. So all I got to do in my calculator is 2.4, which is not what I've written, 2.4 multiplied by 60, and we get 144. Yeah, nice. 144 is my energy in joules. So now I have that energy in joules. Now I have the energy in joules. I have 144 equals 1.2 times by C times by 10. So we're going to simplify with 144. Scales or balance, Q is fine. T equals 12 times C, because 1.2 times 10. So to get C, yeah, beautiful guys, everyone's pros. The opposite of multiplying is we divide both sides by 12. And your calculator, you get a final answer of 12. Nice. 12. Beautiful. And Adele, your units are really close. Molly, good. Yes. Nice. Molly, very good answers. No. Sorry, guys. Is that talk internet, isn't it? Yeah, bad. Maybe we don't have to make it to 2K likes to me to show you my dog then. Maybe I'll show you the dog now. Sophia, that's just because you combined all the equations. That's where it came from. Mohammed always started to no. Yeah, I saw it buffered. I was like, here we go. Yeah, sorry. Ella, normally there's a photo, but they might be cruel and just not give you a photo. Talk internet, yeah. Okay, so 7 marks. We're at 1.5K. Come on, guys. We said 2K to see the dog. But yeah, well, maybe we should show the dog. Right, we'll do one more and then take a break. What do you think? We'll do one more and then take a break. Yes, can we do it? Okay, so this question has came up for the past 2 years. Okay, so I would have said it's unlikely to come up for a third year in a row, but you know, if they done it for 2 years in a row, it might come up for a third year. So again, this was on the 2024 exam and it was on the 2023 exam. So, you know, if they did it twice, maybe they'll do it a third time, but 1.2, that was the mass. Remember, it had to be in kilograms, Kadia? 3K views. Yeah, we're killing it today, aren't we? Is that free GCSEs? Free K views? Are we happy like me? What's the crack? Okay, how do we calculate final temperature? 6 marks. Because technically there will be an answer line that says temperature will be in degrees Celsius. Yeah, so it's higher, combined, and triple. Okay, the temperature of milk increases over time. The initial temperature was 20. The internal energy increased. There's my density, there's my volume, and my specific heat capacity. Hopefully you're thinking, anytime we see specific heat capacity, I'm thinking that equation, energy equals MC, change in temperature. I need to calculate the specific heat capacity. I was given the energy, that's fine, 1000 equals mass times specific heat capacity times the change in temperature. Okay, if we're trying to find the final temperature, clearly we're trying to find the change here. That's the whole point, And I was given the specific heat capacity. So I can even pop in another number in there. I was given the specific heat capacity is 3890. So I need to know the mass. How are we getting the mass? Yes, DDG, good. Right, I've got density and volume here. And if I look at my formula sheet, yeah, beautiful guys. I see an equation that says density is equal to mass divided by volume. Good, good. So the density is 1.04 times 10 to the power of 3 equals whatever the mass is divided by the volume, which is 1.2 times 10 to the power of negative 4. So how do we get the mass? What's the opposite of dividing? Good, guys, right? The opposite of dividing is multiplying. What we do to one side, we have to do to the other. So we're multiplying both sides by 1.2 times 10 to the negative 4, multiplied by 1.2 times 10 to the power of negative 4. Figure out what is that mass. Yeah, guys, beautiful, good. So what we're doing is we're doing 1.04 times 10 to the power of 3. We're multiplying by 1.2 times 10 to the power of negative 4. And we get a mass there of 0.1248. Yep, user, lol is good, except for unit. 0.1248 is our mass. Good, our mass in kilograms. Nice. So now we have the mass, we can pop it back into this equation. So now I have 1000 is equal to 0.1248 times 3890 times the change in temperature. It's all higher, clueless. So 1000 was all aimed at higher, so this would be a higher question only. I'm going to multiply these two together first to get rid of it, or Molly, do it that way, which is perfect too. So what we're doing here is we're doing 0.1248 multiplied by 3890 to make our life easier, which is 485.472. So 485.472 times by the change in temperature. Good. I want change in temperature by itself. So remember, the opposite of multiplying is divide both sides. Good. So I have to, what I do to one side is 485.472. We do to the other side. So divide by 485.472. So hopefully they give you this question again because they've given it for 2 years in a row. And we're going to be pros. So we do 1000 divided by the answer. And we get 2.06. How'd you get 22? How's someone else getting 22? So I got 2.06. So Yeah, so here we have, right, your final answer. Good. Your change in temperature. Good. Yes. Nice. Thank you, guys. That's my change in temperature. That's not the final answer. The final answer said, what is the final temperature of the milk? Yeah, beautiful. Good. So if that is the change in temperature and we started at 20, right? So we started at 20. Yeah, beautiful. We started at 20 and I need to know that it increases. So it's going to end at 22.06 degrees Celsius. Guys, brilliant. No, this is triple and combined. This is triple and combined. Jason, yeah, perfect. Good. Yeah, it was in the AQA paper for the past 2 years in a row. So 2 years in a row, AQA has asked this question. So just make sure you know how to do it, just in case they give it a third year in a row. Again, we don't know what they're going to do, but who would have said they would have given it 2 years in a row? Yeah, it was from an AQA one. So the 1,000 energy was, it's telling us, if it tells us that's how much the energy is increased by, that is the change because it told us how much it's increased by. Ria, we add it because it said the temperature increases, right? If it starts at 20, it has to increase, right? The temperature increases over time. Yeah. Nabil, that we just did there, is it okay? Lori, are we good now? So you deleted your message, so it must be okay. We're at 1.6K. Okay, so before we do energy sources, I think we'll take a quick break because maybe you want to have a look at the slide and try to think about what the next thing is. So take a quick break, maybe give everyone what? You think we'll be good for 5 minutes? We'll give it 5 minutes. So we'll go again at 50. So we'll take just a wee break, 1650. We want 10 minutes. We'll go 5. How about we split the difference? We'll go 7 minutes. There, we split the difference. That's fair. Democracy. We're going to get 1653. There we go. What is that? 1853. I can't read time. Jay, you're right. I can't read time. But yeah, you guys want to see my dog? Bye. Bull, come on. Bull. I think you wanted to bribe him with cheese. Bubba Juke. Bubba, come on. Come here. Come here. Come here. But up. Up. Come on. Come on. Come on. Cheese. Yeah, he's coming. He's got just took me a lot of bribery. Cheese. Good boy. Good boy. Say hello. Say hello. Good boy. Yeah. You guys see him? Look here. No, look here. Look here. Look at him. Say hello. Say hello. Say good luck tomorrow. Yeah, he's a massive Brit. He's a massive Brit. You're not looking at them. You're not looking at them. Yeah, he's a massive Brit. So yeah, he's a big German Shepherd. Look here. Look. Cheese. Food. 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 Yeah, he's a massive Brit. He's a massive Brit. It's called Bubba Juk, Grace. Bubba Juk. Yeah, Bubba Juk. Right, guys, I'm going to run to the bathroom quick. So run to the bathroom, get some water, and we'll come back together in what? 6 minutes now? 6 minutes. Oh, guys, we back. We ready? Anaya, are you back? Yeah, we're ready. Okay, tell me, what's the difference between renewable and non-renewable? What would you write in your exam? Renewable means what? Renewable resources cannot be depleted over time, but non-renewable resources can deplete over time. Yeah, you would get your mark. Can be replenished quickly. Yeah, renewable resources can be replenished quickly, right? The key word there is quickly, right? Because fossil fuels are non-renewable. They take millions of years to form. Uranium from nuclear power stations, again, we have to dig underground for it. So again, that takes ages. So why is a non-renewable resource like burning fossil fuels harmful to the environment? Why is burning non-renewable resources like fossil fuels harmful to the environment? Run out? No. Can be replenished. Another way of saying replenished means replaced. Yeah, beautiful. HYFY. The problem is they produce CO2. Yeah, Mia, good. CO2, hopefully you know from our chemistry exam, is carbon dioxide. Right? The problem with carbon dioxide is, again, it's all in our atmosphere, right? So our atmosphere is that like layer around the earth. So what happens is some of that radiation from the sun is good, right? It's going to keep us warm. But if there's too much carbon dioxide, what happens is some of that radiation is getting absorbed. So instead of it coming towards the earth and then getting reflected back out, it's getting absorbed by that greenhouse gas. So because it's getting all absorbed by the greenhouse gas, it then goes back towards the earth and it causes the whole earth to heat up, right? So it's called the greenhouse effect because it works like a greenhouse. What happened is it causes global warming. It causes the whole world to increase in temperature. And then what are the problems with that? Yeah, this foundation and higher. What is the problem with the whole world increasing in temperature? You might think, oh, it's a good thing if it gets hotter because we live in the UK, right? We want it to be hotter. Yeah, thank you. Rising sea levels, ice cap melting, flooding. Yeah, beautiful. All of this pollution, all of this carbon dioxide in the air is dangerous because again, the global warming is happening. What it causes might cause the ice caps to melt. It causes sea levels to rise. And if the sea levels rise, any land that's close to the sea level is going to get flooded. Yeah, polar bears are sad because they have no homes, right? Because then they want to get food from the water. They get the fish from the water, or they eat seals. But if all of the ice melts, then they've got nowhere that they can rest or sleep to recover. Yeah. So good, good. What are some different things we can do then instead of using our fossil fuels? What are different things we can use instead of using our fossil fuels? How's this physics? Sure, it's all physics. Radiation from the sun, that's physics. Yeah, we can use solar panels. Nice. We can use solar panels. These are renewable energy sources. So that's a renewable one. Be replaced quickly. Good job. We can use hydroelectric or hydroelectricity. Hydroelectric's better. We use that water in your dams. Nice. Again, it's aimed at AQA, but it's for all people. Good. Biofuel. Nice we know what biofuel is. So there's some buses in Bristol that run off biofuel. So they burn either like crops, or they burn animal waste or human waste. And that's how you make them run. Yeah, good. Wind or wind turbines. Good job. Is another one that we can use. Another renewable energy source. One that can be replenished quickly. Yeah, and then the different one is nuclear. And nuclear is the opposite because it is non-renewable. It cannot be replenished easily or quickly. Good, it's non-renewable. What fuel do we use in nuclear power that means that it's non-renewable? Nice. Another one is geothermal. So geo is using the earth, geothermal is using the earth to heat up the energy from the ground, heat up the water using the energy in the ground, using that magma in the earth. Nice, good. We can either write uranium, or you need to know both, plutonium. So nice, people who got both of them. Yeah, uranium or plutonium is the fuel that we use in those nuclear reactors. So you know both. Yeah, another one, instead of another way of using water is our tidal. Yeah, nice. Another way of using the water is our tidal. Yeah, good. Nope, this is combined and triple. Remember we said at the start, combined and triple. So again, it's AQA higher, combined and triple right now. And if you want to subscribe, remember, if you want to type in the chat, you just got to be a subscriber. So you just joined us. Or if you're over on TikTok live and you want to interact and see the stream, just make sure you head over to YouTube. Yeah, YouTube. And if you love my dog or like that you're learning something for free, hit the like button, right? We've got 1.7k likes. We're smashing today. Okay, so where does electricity come from? This can come up in paper 1 or paper 2. Help me out. What is burned heat water? This is my power station. So we're going over our power station right now. How do we get electricity in the first time? So we're moving into electricity now. So yeah, what is the fuel? Yeah, coal. Good job. We can use coal is burned to heat the water. What else? Yeah, the whole thing is called the national grid. Yeah, good job. Yeah, it's fossil fuels, Angie, right? So we can use coal, we can use oil, we can use gas, but the whole thing collectively is called fossil fuels, right? Remember, fossil fuels take millions of years to form, so that's why they're non-renewable. Good. So we heat the coal, oil, gas, and what we do is we heat the water. The water gets heated up. So here's my water. My water gets heated up and it turns into what? Yeah, beautiful, Ella. It turns into steam. Okay, so we got our steam is part B. What does our steam make turn around? What do we call these big things? Think about a big machine that we use. Yeah, they're turbines. Steam turns the turbines. Very like wind turbines, right? Those wind turbines will spin, okay? So very like the wind turbines, they spin. When these wind turbines spin, what are they going to, what's this one here? What do you call that? What does it connect to? Yeah, Fahim, good. It spins the generator. And the generator is then what creates our electricity. In paper 2, you do a bit more about electricity. Okay, what do we call this thing here? It's a step up something. Yeah, beautiful, Yashi. It's a step up transformer. So step up transformer increases that voltage. And then it transfers along these things. What do we call them? The electricity then moves across these things that we call good cables, right? You can't write wires. They don't give you the mark. It has to be cables. So it goes cables to our pylons to our cables. Nice, good. And then those cables go to a step down something. We did energy stores at the start there, just to ask that. Yeah, it goes to a step down transformer. Remember, step down because it decreases the voltage. What does it decrease the voltage to? Yeah, Forp, nice. Bella, nice. Yeah, actually, nice, good. It decreases the voltage to 230 volts. That is the voltage of all UK, right? You need to know that number, so make sure you know that number. Okay, when we get into our homes then, we have these plugs. Okay, so we've got our plugs. We've got these different wires, okay? The blue wire is called which one? The blue wire is our neutral wire. Good. The blue wire is our neutral wire. The brown wire is our live wire, French toe, lovely. And the earth wire is that green and yellow wire. Yeah, good, nice. And what one is the fuse connect to? Hopefully the picture's there to help you out. The fuse is always connected to which wire? Yeah, the live wire. Yes, nice, good job. Grace, nice. Yeah, the live wire, good. The fuse is connected to the live wire, good. Okay, the way I remember it, blue is like the sky. So the sky is blue, so that's why we use one as blue as neutral. The earth is brown, and then the earth is also green and yellow because of the sun. Okay, so this earth is green because of our yellow sun allows photosynthesis. So that's how I remember it. So the earth is green because we have a yellow sun, so that's why the earth wire is green and yellow. Brown is the dirt underneath the soil, and blue is the water in the skies. Nice, people said. The earth wire is for safety. So nice, we said that. And the live wire connect to the fuse. And remember the circuit symbol for a fuse looks like this. Because what does a fuse do? What is a fuse for? So what is that fuse for? Some people said that the live wire is brown because they touch it. That's the color of your pants. I really like that. So the live wire is brown. The live wire is that one that's at 230 volts. So if you touch it, you get electrocuted. Yeah, good job. The live wire is going to break the circuit. Yeah, looks very nice. It's going to melt. So the live wire, if the current ever gets too high, what's going to happen is that live wire will melt. And if it melts, that's going to break the circuit. So if it breaks the circuit, we're going to get no more electricity will flow. So you see we've got a gap here. No more electricity will flow. So that means we don't get electrocuted. The earth wire is there for safety. So the earth wire will, if the fuse doesn't work, let's say, or the wires end up touching the equipment, the fuse wire will take that electricity back towards the earth. Elaine, yeah, that's true. Sienna, what we just said, the fuse there's for safety. The wire will melt if the current ever gets too high. Yeah. The neutral wire is just to complete the circuit. The neutral wire is at 0 volts to complete the circuit. Note the live wire is brown in the UK. Brown in the UK. Okay, so circuits. So this is a little model I use to understand circuits. It's your choice whether you like it or not, but I think it helps out. So I'm just going to talk really quickly. So this is a table. My table's got loads of energy drinks. So let's say it's got loads of Red Bulls, right? Because Red Bull gives you wings. So what happens is my table's got loads of energy, and what I've got is these people walking around my circuit. The people are going to stand for my electrons. You're going to imagine about my electrons are walking through my circuit. So the electrons, they pick up energy from the table. They walk around the circuit, and that's easy, right? They don't have to use any energy for that because they just walk around the circuit. But when they get to something that's hard, when they get to that obstacle, they have to go over the obstacle, but they know, they're smart, they know that there only is one obstacle for them to get through. So to get through as fast as possible, they drink both of their energy cans, and they go back with 0 energy back to the table to pick up more Red Bull. So what we can do then is that I can say that I want to measure the number of people on my assault course. So what we can do is we can put an umpire in the course or an ammeter in our course. So that ammeter is going to tell us the number of people on our course. So let's say 5 people start the race. For safety, if my ammeter is over here now, I need 5 people to end the race. Okay, so what we're saying here is my ammeter measures the current and we make sure the current is the same everywhere. Because what current is the rate of flow of charge. So we're saying is each person here, each electron has a charge because electrons have a charge, and the ampere, the ohmmeter, is measuring the rate of flow of them. It's measuring how many electrons pass them in a 1 second. Now a voltmeter measures the potential difference. So if I put my voltmeter across this component, across this obstacle, it's going to measure the potential difference. It's going to measure the difference in energy, because the potential is energy, what we learned earlier. It's going to measure the difference in energy between 2 points in a circuit. So if it looks at my electron here and it looks at my electron here, they lost 2 cans of energy drink, so it's going to measure a number of 2. Okay, so a voltmeter measures the potential difference, the energy difference between 2 points in a circuit. And that's why we have to connect it across components, or we have to connect it in parallel so we can measure the energy difference between 2 points in a circuit. So Rahi, the potential is the energy. So if I was to put a voltmeter across my cell or my battery that provides energy to the electrons, it's also going to measure 2, because the electron at this point had 0 energy and the electron at this point had 2 cans of energy. So it measures the potential difference, the difference in energy between 2 points in a circuit. Yeah. Okay, so what could this component be? That component, that obstacle could be a bulb. So they might have to lose energy going through the bulb because it comes out light. It might be a fixed resistor because they lose energy when they try to go through a resistor. Okay. And here's me trying to show you what the electrons do. So the electrons again are trying to move through, maybe it's something like a resistor, but what's going to happen is they might end up colliding with all of those metal ions inside those wires. Okay, so those collisions is what happens inside our wires. Gabby, an ammeter, we just said here, measures our current. Okay, so we need to know all of these definitions. So can you tell me which ones they match up to? No, we're not doing circuit components because that's something you need to have locked down, but you can ask me to draw one if you want. So all these definitions you know off by heart. So please take a picture, please learn them. Okay, A2, beautiful. Current is the rate of flow of charge. Okay, that's the definition we need to have down. Current is the rate of flow of charge. Yeah, beautiful, Elaine. The rate of flow of charge. Katie, C to 3, time has to be measured in seconds. Yeah, time is always measured in seconds. Justin, B to 1, potential difference is the difference in energy. Good, because it says potential. Potential is the difference in energy when an electron passes through a component. Good, because remember, it measures the difference in energy of the electron. Lauren, D to 5. D to 5, power, good job, is the energy supplied by the source per second. Remember, power is equal to energy divided by time. Nice. Next one, we're thinking, last one there, E is resistance, is the opposition to the flow of electrons. So we're just on that last picture. If the electrons want to get through, those people want to get through, and someone tries to resist it, they're trying to stop it because there are going to be loads of collisions between those electrons and that metal ions that are locked in place. Again, Annie, here, potential difference is the difference in energy. So just look at your definition there. So to see we've learned it, what is the difference in a series and a parallel circuit? So what we did there before was a series circuit. Series is a single loop, good. So series circuit is like we had in that previous circuit. A series circuit means there was only a single loop. Or what's a better way of saying a single loop? Yeah, Bella, good. Yeah, good. If I was looking at my electrons, a series circuit has only one path for the electrons to flow. Yeah, one path for the electrons to flow. Good. Yeah, and sweetie, good job. A parallel circuit like here has more than one path or multiple paths, more than one path for the electrons to flow, or electrons to move. Sorry, I spelled four there, weird. Okay, so again, hopefully everyone's aware that electrons, they always come out of that longer side that's positive. It's called conventional current, and they go around to that negative side. So here, there's only one way for them to go. But for here, when they come out that positive longer side, at this point, they have a choice. They can either all move through that bulb and go back to where they started, or what they can do is they can all go through the bottom bulb and go back to where they started. So there's a parallel circuit because there's different options for them to take. Okay. So this one question then says, a voltmeter is connected across the battery and read 9 volts. So a voltmeter across this battery read 9 volts. What voltmeter connected across one of the bulbs would read? So what would a voltmeter across this bulb read? What do you think? Pranav says 9. Rashid says 9. Sophie says 9. 999. Beautiful. Yes, it has to say 9. Good job. Because again, think our people. If that potential difference is 9, they picked up 9 cans of energy drink from the cell. So when they get here, they still have 9 cans of energy drink in their hand. But they know they only have one thing to go across because they always go back with 0 energy. So we're going to lose all 9 cans going through that one component. So that's why it's going to read 9. Yeah, beautiful. Good. So it's going to read 9 volts. Nice. Okay, next one. Fill in the missing ammeter readings and voltmeter readings on a series circuit. So remember, series means there's one path for the electrons to flow, right? They all come out of that positive and they all have to go around the bulbs and back. Good. Remember, they don't go through the voltmeters because the voltmeter measures the potential difference, right? The difference in energy. Maybe conventional current, remember, means it comes out of the positive and goes round to the negative. So remember, if you just missed anything, you can always just rewind it a little bit. Okay, so if the cell gives them 49 cans of energy drink, right? Each electron has picked up 49 cans of energy drink. How many are they going to lose going through that first bulb? And how many are they going to lose going through that second bulb? Good, 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 good. Yes, good. right? It can't be 49 because the electron here, with its 49 cans of energy drink, it has to get through both bulbs. If it drank all 49 and had 0 left, it's not going to get through that second bulb. So because it's smart, it says I've got 2 bulbs to get through. So it's going to drink half of them, 24.5, going through the first bulb. And it's going to drink half of them, 24.5, 24.5, getting through that second bulb. Yeah, beautiful. So what we say is they're going to drink half of their energy cans going for each one. So 24.5 volts is each one. Cookie Monster is helping. I'm glad. Good. So remember up here, the electron gained 9 cans of a drink from the cell. They only had 1 component to go through, so they lose all 9 cans. Whereas down here in the series circuit, they've got 2 different bulbs to get through. They can't drink all their cans at the start. They had none left. They have no energy to get through the next one. So they drink half the cans to get through the first one and half the cans to get through the second one. I'm glad this is helping. This sounds good. Yes, we're picking it up. Good, good, good. Lovely. Okay, what about my series circuits again? So here my electrons will come out the positive. 7 of them pass through this point. That's my umpire for safety. They all go through the bulb. How many are going to go back home? What is this ammeter going to read? Yeah, easy. 7 amps, because if I have 7 people who start the race, 7 people have to finish the race. Yeah, current is the same everywhere in a series circuit. Nice. Good. A fuse, we just said before, so scroll back there if you want to look at what the fuse was. Okay, what is my total resistance of the circuit? Angie, yes, good job. Okay, what's my total resistance of my circuit? Yeah, beautiful, guys, good. Because an electron, remember they come out of the positive, because the electron has to go through all 3 of them, right? It's going to feel resistance from all 3 of them. It's going to get slowed down by all 3 of them. So the total resistance is just 6 plus 3 plus 7, which gives us 16 ohms. Nice, 16 ohms. Yeah, beautiful cube core, beautiful Zenith, nice, good. Okay, what is the current? So I want to know, what is this ammeter reading? What is my current coming out of my cell? How do we calculate the current in this equation? So it says V equals I times R. Okay, beautiful, guys. Yes, good. Potential difference. It tells me each electron is gaining 6 cans in a drink. So 6 equals some current times the resistance is 16. To get the current by itself, we'd think, what's the opposite of multiplying by 16? The opposite of multiplying by 16 is divided by 16. So what we do to one side, we do to the other. So we're doing a 6 divided by 16. Reality, good job. Lovely. So hopefully that's what everyone did in our calculators. 6 divided by 16 gives me a final answer of 0.375. Lovely. 0.375. And current is always measured in, Riley, beautiful, amps. Nice. Megan asked me about that at the end because it's more of a triple thing. 0.375 amps. Nice. Right, last question. What is the potential difference across the 6 ohm resistor? So hopefully you're thinking, I want to know the potential difference across the 6 ohm resistor. So remember what that means is, I want to find the difference in energy between an electron before it goes in versus after it goes in. Riella, that's so lovely to read that you find it helpful. So what I'm doing is I'm connecting a voltmeter across those 2 points to measure the potential difference, the difference in energy between those 2 points in that circuit. I know that V equals I times R. So to find V, I know the current. Remember, the current we just calculated. The current was 0.375. Oops. Beautiful, guys. Good. 0.375. And the resistance, we only care about that one resistor. So the resistance is 6. So do 0.375 times by 6. And we get, hopefully same as all you guys, 2.25 volts. Beautiful. Alana, nice. Jude, Fatima, nice. Abel, nice. Good. So what we're getting there is 2.25 volts. Good. Nice. Easy. Riri, good. Thomas, good. Cookie Monster, good. Yes. Nice. Right. Some people wanted some circuit symbols. So you wanted required practicals. Here we go again. It says copper wires can be called ohmic conductors because they obey Ohm's law. As the current increases, the potential difference increases. They are directly proportional. How do I know that they're directly proportional from looking at this graph? What do you see? How do we know they're directly proportional? Sophie displayed all your subjects to you. Oh, I love it. How do we know they're directly proportional from looking at this graph? Origin, beautiful straight line, nice. Because we can see that it is a straight line that passes through the origin. And that origin there is just that 0, 0 point. Doesn't matter what topic it is. It could be Hooke's law. It could be electricity. If you get any graph at all where you have a straight line that goes through that 0, 0 mark, the answer always is that the relationship or how they are compared is that they are directly proportional. Okay? Okay, ones that you need to know about that don't obey Ohm's law. Harvey, this is Ohm's law here. This is Ohm's law, what's in bold. Ohm's law is that equation V equals IR. As the current increases, the potential difference increases. They are directly proportional. That's what Ohm's law is. Okay, these ones are non-ohmic conductors. Can you list them, please? What are they called? Angie, lovely. Tiana, lovely. This one is a diode. What's the next one? Yeah, diode. Let's label them B, C, and D. What's B, C, and D? Thermistor, L, LDR, and a bulb. Yeah, beautiful. L, perfect. Lovely, guys. Yeah, this one is a thermistor. Lovely. This one looks like a resistor, but it's got light rays hitting it. So that's why it's going to be light rays hitting it. Good job. So it's a light dependent resistor, right? Because it's got light rays hitting it and it's a resistor, light dependent resistor. Good. And this one you can call a bulb or you can call a filament lamp. Nice. Good. Okay. What is a diode? Why does it look like that? What does it mean? What does a diode do? No, a variable resistor looks like that. That is a variable resistor. So they're completely different. So variable resistance different. Tima, we're going to talk about them in a second now. So what's a diode? Yeah, beautiful, lovely. A diode only lets current flow in one direction, like 1D, one direction. And you need to know how to sketch a graph for a diode. So for a diode, that is the graph that goes like this. So that's your diode, the graph like this. Okay, what is a thermistor? What does it do? It's got the word ther in it. What does you can relate it to? What is a thermistor? Thermistor. The band One Direction, yeah. What is a thermistor? Good job. A thermistor has to do with temperature. So remember, a thermistor was designed to be the opposite. So what do we compare it to? Yeah, it's resistance. Good. We compare it to the resistance. So if the resistance is low, what's going to happen to the temperature? If the resistance is low, what happens to the temperature? Remember, they're designed to be the opposite of everything else. Yeah, beautiful, Jay. If the resistance is low, the temperature is high. They're designed to be the opposite. Good. LDR, that's a paper 2 one. Okay, what about this one? This is a light dependent resistor. What is it made to be? It's made to be the opposite. It's affected by light. So let's say the lights are really bright. What happens to the resistance? If the lights are really bright, yeah, Bella, beautiful, the resistance is going to be low. Lauren, good, good. Ola, good. Riley, good. Lovely. If the light is bright, the resistance is low. So just remember, these two are designed to be the opposite of everything else that you've learned. Yes, Mia, and we need to know a graph for a filament lamp. How I remember a bulb or a filament lamp that you need to draw a graph for is, again, if you draw like a fancy F, you know, like a cursive F, it's a fancy F. So that there is going to be your x-axis. So if I had to draw a graph for a filament bulb, you just kind of draw like your fancy F over it. You see that's like a fancy F? Yeah, like kind of like an S, but I remember like a fancy F for like filament bulbs. Yeah. Megan, switch direction of the battery just means if my battery was connected this way, will my bulb light up? Yes or no? Everyone tell me in the chat. If my battery is connected this way, is my bulb going to light up? Will the bulb light? Yes or no? Yeah, good. The bulb will light. Yes, because the conventional current. Remember, current comes out that positive. The diode only lets it go one way. So look, the arrow shows us the way it lets it go. So that arrow shows me the way it can go. So the current can get through it and it can go into the bulb. But if I switch the bulb, so let's say we switch the bulb around, not the bulb, sorry. If I switch the battery around, someone says, what does it mean to switch the connections of my battery? Tell me now, will the bulb light? Will we do a poll? Will the bulb light? Is it going to be yes or is it going to be no? Is my bulb going to light in option 2? There should be a poll there. 5, 4, 3, 2, 1. How are we feeling? 83% of us are correct. No. So this bulb will not light because look, what's happening here. Remember, electrons, they only come out that positive. So they come out the positive, they're moving this direction. You might think they go for the bulb, but this diode blocks them, right? Look, the diode only lets current go that way. It's not going to let the electrons go this way. So that bulb is not going to light up because, again, the diode only lets current flow in one direction. Okay? The diode only lets current flow in one direction. That's why here we see that it's 0 over in this side. Good. Resistance, we did a resistance earlier if you want to look back in the chat there. Okay, tell me again, what's a diode? What is a diode? Yeah, beautiful. Good job. It only lets current flow in one direction. Right, we need to know this off by heart. Beautiful, one direction. How would I sketch a circuit to show the current and potential difference through a diode? So how would you sketch a circuit to show the current and potential difference through a diode? What do we need inside our circuit? So here the arrow, do you see? It looks like an arrow pointing in that direction. Okay, I need wires. What else I need? Oh, like, yeah, I need a battery or I need a cell. So we do a battery, we're going to do 2. Okay, I want to look at a diode. So I'm going to draw my diode, which one lets current flow in one direction. What else do we need in a circuit? Good. I need an ammeter because I need to measure the current. Good. What else I need in my circuit? I need a voltmeter. Beautiful. Where am I going to put the voltmeter? Hope you're thinking, where's the voltmeter going? The voltmeter has to go across the thing we care about. We care about the diode. So I'm going to put the voltmeter across, yeah, beautiful guys, across that diode. The voltmeter goes in parallels, we call it, across my diode. Nice, good. Okay, is that finished? What do you think? Is that enough? What have I missed? I've missed something. Thank you, S. Good. What we need is a variable resistor. I need a variable resistor so that I can change the resistance, so I can get lots of readings of my current and my ammeter. Because if I just plot a table of those results of what my current said on my ammeter in amps and what my voltmeter said of my potential difference, I can't just get 2 values. I need lots of values. So the way to get lots of values is to use a variable resistor so that I can change the resistance. Nice, we said we should have a switch. Probably should have a switch. Why is it good to have a switch? Why should I include a switch? What does a switch prevent happening? Why should we include a switch? Why should we include a switch? Good, nice. To prevent, that was very good. I can't remember, I saw your name and you went away too quickly. Yeah, good job, Sadine. To prevent the wires from overheating. Nice, good job. So some of you are asking a lot of questions about like little things that I kind of assumed you know. Some people said there, why do we need a variable resistor? I did say, so we know that we can change the resistance. So hopefully some of you might be thinking right now, I want to go more into what a variable resistor is, but that's the beauty of this, right? You can watch this again later. We're going to end at 8:30 and then you've got the rest of the evening to look back at the bit of this lesson that you didn't quite get and then read your textbook on that little bit again, okay? So that's the beauty of this, right? You can watch this anytime you want after. You can maybe wake up in the morning and watch that little bit of this video again. So don't be stressing too much right now if there's something you're like, whoa, that went a bit quick, I didn't get it, because it's all recorded, right? You can watch it anytime you need again. And then maybe after this lesson, you probably just revise that little bit you struggled with, and then you can go back and watch the lesson again, yeah? Okay, how do we sketch a graph of the results? Hopefully everyone remembers the diode. What do we draw as a diode? Remember that the current is 0 because it only lets it flow in one direction. So that would be a sketch of my graph. And why is it not then an ohmic conductor? Yeah, beautiful pinch at no, it's not an ohmic conductor, so it's not that. Why is it not an ohmic conductor? Yeah, beautiful, Alana. That's a nice way to say it. It's not an ohmic conductor because the current and the potential difference. Beautiful, guys. Good. Are not directly proportional. Remember we said they had to be directly proportional if it was a straight line through the origin. Tamin, that's what we just said there. Remember, if it's an ohmic conductor, it's always going to be a straight line through the origin. But because this is not an ohmic conductor, it doesn't follow that relationship. It's not going to be a straight line through the origin. Yeah, because it's not an ohmic conductor, Amelie. Okay, everyone think slowly about this one now. So it says, what happens to the potential difference across R as the light intensity decreases? We'll do another poll. So what are you going to pick as your answer? Is it going to increase? Is it going to decrease? What is the option? What are you thinking? So what happens to the potential difference across R? Potential difference across R means we're putting a voltmeter across R. And what it's doing, it's measuring the difference in energy, remember, between those 2 points in that circuit, saying how much energy does the electron have before the resistor versus after the resistor. Hello all, we kind of did that at the start. If you need to go for it again, ask me at the end. Okay, so hopefully everyone thinks this is a light dependent resistor because I've got light rays hitting it. First thing we're thinking is light intensity decreases. So the light intensity is dropping. The first thing you think is what is happening to the resistance? They give you 5 seconds. 4, 3, 2, 1. Okay, so I have 70%. Oh, 69% says increase. So we had 69% said that it's going to increase. Okay, let's see. If the light intensity decreases, we know that means the resistance we just learned is going to increase. Okay, but this resistance stays the same. So hopefully you're thinking the resistance of the whole circuit increases. So my resistance has increases. So I think what's going to happen to my current? So think about the current that's moving through here. If the resistance has increased, I've made it much harder for those electrons to get through, right? I made it much harder for the electrons to get through. If it's harder for the electrons to get through, the current is going to decrease. Okay, so we know the current decreases. So now I'm thinking, what's happening to the potential difference here? V equals I times by R. The potential difference equals the current times the resistance. This resistance hasn't changed. This resistance is the same. But you've just told me the current decreases. So if the current decreases, what happens to the potential difference? The potential difference is going to decrease. So hopefully you see that 69% of you were wrong. It was only 31% of you who would have got this correct in your exam, okay? So 31% of you, you're smashing it for tomorrow. The 69% of you might want to watch that again slowly or go back to the electricity part, okay? So remember what we said was you have to think through it step by step. Don't rush these. Think through step by step about what we said is going to happen each time, okay? Okay, next one. What is Ohm's law? We should be pros at this because we've done it so many times. So can you pop it in the poll? What's the answer? We're good. Right, what is Ohm's law? Let's get 100%. Come on, guys. We did this like 8 times. I believe in you. 5, 4, 3, 2, 1. 89% of us are perfect, or 90% of us, good. Ohm's law is that current is directly proportional to the potential difference. Remember, we see it because it's a straight line that goes through the origin. The current is directly proportional to the potential difference. That's how we got that equation, V equals IR. Nice. Right, next one. What is that a graph of? Again, we need to be pros at this for tomorrow. So hopefully we're seeing right now, have we learnt this? Were we listening well? Do we need to watch that little bit of the video again? GB Ross, can you stop writing good girl? I don't know why, but it like really annoys me. Good girl is like really demeaning. Okay, right, next one. What's this a graph of? 5, 4, 3. Alex, again, just watch it back in your own time. 3, 2, 1. So you might just need to watch it back slowly again. Just listen to each word carefully. Okay, 82% said it's an ohmic conductor. Beautiful. It is an ohmic conductor. Thank you for my 82%. Because an ohmic conductor, remember, is always a straight line through the origin because they are directly proportional, right? They're directly proportional. Bansat, don't you start. Next one. Density. An object is put in water. It has a mass of 12.8 kilograms and a volume of 4 meters cubed. The density of water is 1,000 kilograms per meter cubed. How do we calculate its density? Hopefully you're pros because we did this earlier. Gabby, lovely. I can see my formula sheet. Density is equal to mass divided by volume. Good. So the mass, they were kind to us, is already in kilograms. The volume is 4. So what do you get? What's our density? GB Ross. Johanna, thank you for units. Good. 3.2 mass is in kilograms, and we divide it by a meter cubed. Nice. Okay, will it sink or float? Will it sink or float? Good. Thank you. Yes, we got it. It's going to float. Nice. Because the density of water is given to you there. This one, because it is less dense than water, it will float. Nice. Good. So I'm just checking. You remember that if something, you compare the numbers. So it's less, sorry, if it's less dense than water, it's going to float. Nice. So when reading the volume on a measuring cylinder, what type of error do we need to avoid? Good, Masson. Thank you. Masson, hello. Welcome. Parallax error. Good. Parallax error. Good. Is there anyone? Yeah. Parallax level error is what we call reading from eye level. Good. So what that means is, oh, and I like that. Someone wrote there about meniscus. We also need to read from the bottom of the meniscus, but that's not a type of error. Okay, so what is parallax error? Let's say I was reading the volume here, or the volume of my water bottle. I need to make sure I'm at eye level, right? I want to read it at eye level. But reading it at eye level is what you're supposed to do. The thing you're supposed to avoid is parallax error. Because if I was to read it from up here, I'm going to get a number that's too low. If I was to read it from down here, I'm going to get a number that's too high. So that's why what you need to do is to avoid this. So avoiding that is called parallax error. So you want to avoid parallax error. Good. Okay, next one. What is the resolution of my measuring cylinder? So some people weren't happy about resolution earlier. So look at my measuring cylinder. What is its resolution? Remember we said on a ruler, the smallest number was 1 millimeter. Zara, perfect. Stormzy, perfect. Good. The smallest number I can see here is 50. There's 50, 100. There's 150. The smallest reading is going to be my 50 milliliters. You could say 50 millimeters, or you could say 50 centimeter cubed, whatever you want, because it says milliliters here and it says centimeter cubed here. Nice. The smallest reading you can see on your device. Gabrielle, because 0 is not a number. 0 is the absence of numbers. It's nothing, right? 0 is just nothing. It's not a number, it's just nothing. Okay, when reading the mass of the liquid, what type of error do we need to avoid? So what type of error do we avoid? Yes, Yashi, good job. It's called the zero error. Good. We go with the zero error. For example, if I was to weigh myself, I'm not going to get on the scales when it says 0.1 because then I'm going to get the wrong reading. Okay, I'm going to make sure that I'm going to tap my toe on the scale, make sure it says 0, and then I'm going to get on the scale and see if I've gained weight or lost weight, right? So we call that the zero error. If you write your exam, make sure it says 0, you're not going to get any marks, right? We have to call it the zero error. Sophia, you're talking about something else. We'll come to it in a second. Random error is something that you do wrong. I see people, random error is something that the human does wrong, or you might say it called human error. So that one might be if you're timing something and you get distracted and you forget to stop the timer. A systematic error is something wrong with the system. So a systematic error could be that it's not calibrated properly. It could be what we said here, that zero error, that it doesn't say 0 before we start. So systematic error is something wrong with the system. Yeah. Right. Next one. This one, now we're getting on to atomic structure. So it says, The graph on the right shows the heating curve of water obtained from an experiment. Ice was heated with a 200-watt electric heater. What happens to the kinetic and the potential energies between 100 and 200 seconds? So here's 100, here's a 200. What is happening to the kinetic and the potential energies? Riri, good job. What about the potential? Oh, very good, Pranav. Very good. A lot of us are really are happy with kinetic energy, but you've not told me about potential energy. Good job, Moonlight. Yes, nice. So here we can see what's happening. Look at my temperature. My temperature is being increased. So for question I, because the temperature is being increased, we know then that means that the kinetic energy is being increased. Nice, guys, is being increased. We're at 1.8K likes. We've nearly hit the 2K goal. 2,000. We've nearly got there. Okay, so the temperature's increased, the kinetic energy's increased. Everyone's good about that. Yeah, good job, Riri. It asks us about the potential energy, but the potential energy is going to stay the same. Okay, it's going to stay the same. Someone said there, what is potential energy? Okay, potential energy, it tells us how far apart the molecules are. So for example, if I have a solid, so there's my solid, it's got a really low potential energy because the particles are really close together. If I've got a gas, it's got a really high potential energy because the particles are really far away. So that's what potential energy is. It tells us how far away the particles are. Same like gravitational potential energy. The further you are from the center of the earth, the more potential energy you have. So just remember, if you're trying to type in the chat and you've joined us late, you just have to be a subscriber if you want to type in the chat. No, Megan, they really like you to be specific. If they ask you about a scale, you have to say 0 where. Louis, no, I'm from the north of Ireland. Internal energy, Ali, is the sum of the kinetic energy and the potential energy. Zach, why so many sad faces? What's the crack with you? Are those angry faces? Yes, it is, Amanda. Good job. That's where we're coming to now. So what is the energy transferred while the water is boiling? Okay, so what Amanda said there is, we know it's boiling because boiling is a change in state. And hopefully we're doing what Amanda said. Amanda said we know that change of state occurs when the line is flat. So I've got two parts here. The line is flat, part A and part B. So to think out which one of those is boiling, right? Which one of those is boiling? Hopefully you're thinking boiling is when the change of state, when someone goes from a liquid into a gas. So boiling is going to be over here, right? This one is boiling. It's going from my liquid into my gas. So what I do is I want to look at the boiling temperatures. So if I go down, I can see it started boiling at 300 seconds and it stopped boiling at 600 seconds. So what is the energy transferred while it's boiling? How do we calculate this? I'm seeing 300, I'm seeing 60,000, I'm seeing 300, I'm seeing 60,000. Yeah, Ella, good job. So Ella just answered someone else's question there. To increase the potential energy, we change the state. So anytime there's a change in state, that's when the potential energy is increasing. And the kinetic energy stays the same because the temperature isn't changing. Good, nice. So hopefully everyone saw I was given a power and I want to know an energy. So power is equal to energy divided by time, or work done divided by time. The power it told me was 200. I need to find the energy, and the time, hopefully everyone sees there, is 300 seconds, right? It starts at 300 and it ends at 600. So that time there is my 300 seconds. So to get energy by itself, I think, how do I do that? I have to get rid of the 300. The opposite of 300, the opposite of dividing is multiplying. So what we have to do is we multiply both sides. What we do to one, do we do the other. And that's how we end up getting 60,000. Beautiful. And the units, mass, and thank you, are joules. 60,000 joules. Good. 60,000 joules. Rashid, 200, because it told us up here, 200 watts. It told you that in the question. 200 watts. 200 watts. Lamisa, I agree. Let's get 2K. We're at 1.9K. Right, next one. A block of ice is removed from a freezer where it was kept at negative 18 degrees Celsius. What's the changes in arrangement, movement, and energy as the block warms up to melting point and then melts? Chelsea, how does the kinetic energy change? What visible things occur? What do you mean visible things, Chelsea? Technically, you wouldn't see it. You just see that it gets warmer. So as things increase in temperature, you might put a thermometer in it and you want to look at the thermometer increase in temperature. That's probably how you could see it. Hazel, for joules, has to be a capital J. Has to be capital for joules. Hello, Al. Again, I saw you written that a few times through the chat. We'll do it at the end. How many marks would it be? It depends. It depends how nice they're being. It could be 4, it could be 6. But again, are we going to write an essay or bullet points? Hope you're thinking physics, bullet point it, right? Bullet point it. Okay, so it says, block of ice is removed from a freezer. So I got ice at negative 18 degrees Celsius. I want to warm it up to its melting point and it melts. What temperature does ice melt at? What temperature does ice melt at? Yeah, 2K likes. We made it. We made it. Bubba, come celebrate. Bubba's like, I ain't moving. I'll let you guys see Bubba because he's not moving. You can watch his little, he's guarding. He's like having a little, he's having a little time. Bubba. Bubba. No, he's done. He's done with you guys. He doesn't care. He doesn't care about my 2K likes. He's like, leave me alone unless you're going to feed me. He's hungry. I have to feed him after. He needs fed. Okay, nice. Everyone knows that ice melts at 0 degrees Celsius, and that's a number you have to remember, 0 degrees Celsius. Okay? So what it says was, describe the changes in arrangement, movement, and energy. Okay? Harvey, feed him now. He's grand. He's not starving. He's just lazy when he's hungry. Okay, so it says, describe the changes in arrangement. Okay, so what we're thinking is, ice right now is a solid. So how is the solid particles arranged and how are they moving? No, it says it starts at negative 18. So when you talk about how they're arranged and how they're moving. So, Sophie, a solid has a regular arrangement with particles that are fixed and vibrate in spot. When the temperature increases, it gives the solid kinetic energy, which means more frequent collisions. Sophie, that's quite nice. Nice. We're going to start with that. So Sophie said, we know solids, when it's at negative 18 degrees, solids have a regular arrangement. And we know that they are vibrating. So beautiful of you thought about mentioning vibrating. They vibrate on the spot. Okay, so what we're doing as we heat it up, we know that the temperature is going to increase. And hopefully everyone thought it asks us about energy. As the temperature increases, what energy increases? And we're saying what Sophie says, the kinetic energy increases. Beautiful. Once we get to 0 degrees Celsius, we're going to say that there's a change in state. So what are we saying here? What's the next bit to add what Sophie said? Once there's a change in state, what's going to happen? George Brown, at the very start, if you download the work pack, there's QR codes there for you to get it. Good job. The change in state, nice people thought the intermolecular forces break, or we say that the potential energy increases, right? Because what happened is we're breaking those bonds. We're moving the particles from their solid arrangement, from that regular arrangement, and we're changing them into liquids where they're able to free to move over each other. So that's why their potential energy increases, because we've let them be slightly further apart. So I talk about their arrangement and movement. We can now say that they're in an irregular arrangement and they can move over each other. Hello all. Yeah, the internal energy has increased the whole time. The internal energy has increased the whole time. George, there's no equations that aren't given. There's no equations that aren't given. There's no equations that aren't given. The kinetic energy stays the same during a change in state. All right, because during a change in state, there's no change in temperature. Kinetic energy only changes when there's a change in temperature. Yeah. Yeah. How many monitors I'm using? 2. Right, good guys. This question came up kind of a little bit last year, but it's not come up in a while. So just go over it to make sure you're good, right? So just go over to make sure you're good. Okay, radiation, probably the best topic. In it, everybody has to learn that water ice melts at 0 degrees Celsius and it boils at 100 degrees Celsius. Just facts that you need to know. Yeah, it's facts that you need to know. Okay, we're getting into the nuclear topic now. Two differences in the nuclear model and the plum pudding model. Yes, Sophie, what we said was if it changes state, if there's a change in state, the potential energy increases, but the kinetic energy stays the same. So Sophie, we talked about that when we looked at the graph. So maybe at the end, you just go back to that little bit and watch it again. Okay, the nuclear model has neutrons. Nope, don't like that. That's not going to get any marks. The nuclear model has a what? The nuclear model has a nucleus. Thank you, L. Okay, differences, but the plum pudding model, flip, good, does not. Good. What else was in? Nuclear model has orbitals with electrons orbiting it, where plum pudding model, the electrons are embedded. Krishy, that's beautiful. Good job. The nuclear model. So in the nuclear model, electrons orbit the nucleus, but in the plum pudding, electrons are embedded. Are we doing chemistry now? No, this is in chemistry and in physics. Yeah, Kitty, that's a nice one. The nuclear model is mainly empty space. That's a nice one. It's mainly empty space. Whereas the plum pudding model is a solid mass, right? So that's different. So one's mainly empty space, one is a solid mass. What else are we saying? Yeah, one's got shells of electrons. That's nice. Yeah, Sophie was the empty space. Yeah, good. The solid mass. Nice. Yeah, yeah, beautiful. Good. Easy, right? It's an easy one. Good. Perfect. Okay, next thing. Yeah, you can just look at the diagram to help you out. But yeah, you just have to learn that off as well, Sophie. Okay, so this one, if you look at the periodic table, which you don't get in your physics exam, you can see that uranium is super large, right? Because hydrogen is 1, 1. Uranium, look, is 238 times bigger, okay? So uranium is a really large nucleus, and because it's unstable, so what it wants to do is it wants to get smaller. And that's how what we call radiation. It wants to get smaller, so it emits something in order to get smaller. And we know that we call this decay. So remember, think about biology. If something decays, it breaks down. So what we're saying is if this decays, it's going to break down. And we will record this decay using a Geiger tube, or sometimes you'll see it called a GM tube. And basically, it's kind of like a metal detector. So maybe like you're walking along and you see metal, it goes like beep, 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 and you know there's a metal there. So that's where you know to stop and pick up that that's where you know there's loads of like stop and pick the metal, or there's loads of radiation there. Okay. And radiation is measured in this thing called becquerels. Okay, again, that's something you need to know. It's just a capital B and a small q. It's measured in becquerels. Okay, so Katie, thank you. The question up here was, how many protons, neutrons, and electrons are inside this atom? We need to know this for physics. And you just had chemistry, so hopefully they're pros. Good, Bella. And good, Katie. The bottom number is always the number of protons. Okay, you have to remember that in physics. So the number of protons is 92. How do we calculate the number of neutrons? Oh, use your calculator. Someone wants to get different numbers here. Yeah, arrow, good, nice. The number of neutrons, we just do a bit of math. We do 238. Take away 92. Yeah, lovely. And we're going to get 146. 146 neutrons. Good. And how many electrons are there then? How do we figure the electrons? Yeah, Mohammed, nice. If I have 92 positive protons, I'm going to have 92 negative electrons to balance it, because it is an atom. Remember, atoms always have equal numbers of positive protons and negative electrons. Nice, good job, Nicola. Yes. Okay, what are the 3 types of radiation that this uranium might emit in order to become more stable? Yep, L, beautiful. And I saw loads of people wrote it earlier. The 3 types are alpha, beta, and gamma. In order of decreasing ionization, beautiful, everyone wrote that, it's alpha, beta, or gamma. A question that might come up, and you're probably thinking right now, what is ionization? And what would you write in your test if I asked you what ionization is? What would you write in your test if I asked you what ionization was? Yeah, Pranav, beautiful. Oh, Arrow, no, you wouldn't got the mark. Minty, you wouldn't got the mark. You would have got the mark, Dan. Good job. Amelia, you would have got the mark. Good job. Ah, nope, sorry, Amelia, you wouldn't. Blugs, logs, above, you would have. No, Harvey, again, you wouldn't have got it. So ionization, they really care about how you write it. You have to write, yeah, Bella, I loved it. You have to write it's the loss or gain of electrons. All right, that's what ionization is. Think about ions from your chemistry test. Remember, ions is a loss or gain of electrons. So if an atom becomes an ion, it either lost or gained electrons. Yeah, lost or gained electrons. It's good. Okay, which type of radiation is the most penetrating? We'll do a poll. Is it A, is it B, or is it C? Go. Which type of radiation is the most penetrating? Use my pictures to help you out. 5, 4, 3, 2, 1. 85% of us are pros. Yes, and we shouldn't really be a pro. Guys, this is all the slides. Come on, we just had a look at the picture. Most penetrating means which one can travel the furthest. Okay, but that's how it'll look in your test. Which one can travel the furthest? So I look at alpha. Alpha can't get free paper. Look, it's stopped by paper. Beta can get free paper, but it's stopped by that aluminium. Gamma can get free paper. It can get aluminium, but it's reduced by the lead. So clearly our gamma is the one that can travel the furthest. It is the most penetrating. Yeah, gamma is just energy, Abu. Yeah, it's just energy. It's just a type of energy. Okay, let's get 100%. Which one, A, B, or C in my poll is the most ionizing? Which one is the most ionizing? Okay, 5, 4, 3, 2, 1. Yeah, good. Lovely. Alpha radiation is the most ionizing. Remember, ionization is the loss or gain of electrons. Sophia, yes, you do. We'll talk about it in a second. Alpha is the most ionizing because it has the biggest charge. Can anyone help out? What is the charge of an alpha particle? What is the charge of an alpha particle? Isabel. Beautiful. I can see down here it's got 2 protons. Yeah, nice, Jay. Nice, Yiwong. Good job. It's got 2 protons. Remember, be positive like a proton. A proton has a +1 charge. So if I have 2 of them, it's going to have a +2 charge. So it's the most ionizing because it's got the biggest charge. What is the charge of a beta? What is beta? What is the charge of a beta? What is the charge of a beta? Good. Beta is a -1 charge because remember what it is it's a fast moving electron. Good. It's a fast moving electron. Nice. Okay. Someone asked this question a minute ago. Which type of radiation, A, B, or C, is stopped by 5 centimeters of air? Which type of radiation is stopped by 5 centimeters of air? So like 5 centimeters is like this much. Can't even travel 5 centimeters in air. We're going to have a break in 10 minutes. 5, 4, 3, 2. Yeah, this is foundation and higher. 88% of you are perfect. Good job. Alpha radiation can stop by 5 centimeters of air. Alpha radiation can't even travel 5 centimeters in air. That's why it can't get through paper. But beta radiation can roughly travel 1 meter in air. That's why it can get through paper. And gamma can travel infinity distance in air because it's just an EM wave. It's just radiation. What is an alpha particle also known as? So it says it's got a charge of +2, but what is it? If beta is an electron, what is alpha? What is alpha? Oh, it's not helium. Careful. If you put helium, you're wrong. There's so many heliums here. Stop. SOS. Alert. It is not helium. Helium is wrong in your test. They will mark that wrong. It is a helium nucleus. Be careful, please. Careful, careful. Loads of you there wrote helium. It's helium, it's make sure you say helium nucleus. Helium nucleus, remember, it's because there isn't any electrons. It's not an atom. There isn't electrons. Why are you stingy? It's not stingy. It's wrong or right. A helium atom has got 2 protons, 2 neutrons, and 2 electrons. That's the helium atom. But the alpha particle doesn't have any electrons. It's just the nucleus. Okay, please be careful. That's like a really common mistake. The atom is neutral because it has 2 protons and 2 electrons. That one is neutral. But the nucleus has got a charge of +2 because it only has those 2 protons. Yeah, so this is alpha. Yeah, that's my little symbol for alpha. It's like a little fish. So it's my alpha. Yeah. Okay. What are my missing numbers? Can you tell me what A is and what is B in the chat? Let's get rid of green. I'm tired of green. What is the numbers A and what's numbers B in the chat? So I'm seeing loads of 231 from Yasin, from Masin, from Zara, Reese, 231, Tabby, 231, Hairstyles by Beth is 231. What are we saying for B? Seeing a lot of 91s, 91 from Brian, 92 from Ella, 91 from Ola. I'm seeing 89 from Sadia. Okay, so yeah, the most choice here is 91, and that's correct. Yeah, both are correct. Okay, so how do you do it? Helium nucleus is an alpha particle. Remember, you have to know these numbers off by heart. Okay, so this was checking, have you learned those numbers? The numbers are 4, 2. Please learn those numbers, 4, 2. The top number here is 235. So the top number here has to also be 235. If this number is 4, that one has to be 231. The bottom number here is 92. So the bottom number here has to also be 92, which it is. An electron, remember, that's beta radiation. So this was alpha, that's beta. Remember, beta is a fast-moving electron. We need to learn the numbers. An electron has 0 mass, but it has a -1 charge. So the numbers there are 0, -1. So over here, I've got 234. So over here, I need a total of 234, which I do have. Over here, I have 90. So over here, I need a total of 90. So I had to think, what plus -1 gives me 90? And that's how we figured out it had to be 91, right? Because beta is a fast-moving electron. Yeah, DDG. Beta is a fast-moving electron. Amar, that's a really good observation. It gains a proton because you don't need to know this, it's A level, but what actually happens is beta radiation is because one of the neutrons inside the nucleus changed into a proton. But you don't need to know that for your GCSEs. It's more of an A level one, but really nice that you spot it. That's what's actually happening. Yeah. Justin the Gamer, I love that. Okay, next one. What is my half-life? Okay, people try to make this so difficult. It's so easy and it's lovely, right? That's why we kept it for the end because it's a lovely topic. Half-life means the time to drop by half. Your life is a time. So half-life is the time dropped by half. Please put units in, Margaret. Yep, Bella, lovely. Units, 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 units. Got 10 seconds, I got 20 seconds. Half-life. So half-life is the time to drop by half. So at the start, at 0 seconds, I have 100 becquerels. So what I want to find is where 50 becquerels is. So I go across and I go down. So what's that number? 10 seconds. So the half-life, the time for it to drop by half, is 10 seconds. So look, if we do another 10 seconds, it's going to drop to 25. Right? So half-life is the time to drop by half. Activity just tells us how many, so it's telling us how many particles are emitted. So let's say we've got uranium-235. Let's say it emits, what it's saying is over 10 seconds, it's emitting maybe 50 alpha particles, right? The activity is like how many radiation are we detected in that 10 seconds? Yeah. Okay. This person says the half-life is 2 seconds. Are they right or are they wrong? Aisha, I do know. It is Megan. Yes, good job. Riri, good job. It is wrong. Why? Ham's 1 what? Yeah, good. Nice. So are we all saying it's 1 second? Kitty, thank you. Yeah, a few of you got there. It's 1 hour. Please look at your units. Check your units. Careful. Watch your units. Look at your units. So if it starts at 100, I want to see half-life, the time drop by half. There's 50. I go down and I can see that it's 1, but the time here is an hour. So careful. Watch your units. Watch your unit. Brooke does art. What's your units? What's your units? Okay, guys, we have last slide left for triple, or last slide left for combined. Let's kill it. What type of radiation was emitted by Magnesium-241? What type of radiation? We can do this. Smash it. I'll take 3 more minutes of your time. Theo, beautiful. How do we know it? It is alpha. We know it's alpha because alpha cannot get free paper. Look, all of this radiation is stopped by the paper, so we know it has to be alpha radiation. Nice. How come that's not hurting anyone? If there's alpha radiation in smoke alarms, why is no one getting hurt? If there's alpha radiation in smoke alarms, why is no one getting hurt? Okay, nice, Tom. It can get for your skin, but then I might get skin cancer. But why am I not getting hurt? Yes, nice. Thank you for writing 5 centimeters. Nice. Because it can only travel 5 centimeters in air, right? It is the least penetrating. So if I'm in my house, here's my house, and here's me down here, happy reading my dinner, and here's my smoke alarm up here, I'm never going to get sick because that's alpha radiation. It can only travel about 5 centimeters, right? It's never going to make me sick. And also, what are your smoke alarms encased in? Hopefully everyone knows they're encased in plastic, right? So if alpha radiation can't get through paper, they're never going to get through plastic either, right? So they can't even get outside of the smoke alarm. Yeah. Guys, that was awesome. Okay. Please, last thing, because some of you are like, oh, what do I do now the rest of the night? If you scan this, we are going to give you a free revision resource, okay? And you will like it, I promise. So please scan the QR code, get your free revision resource, and it's something for you to check. Are you ready for tomorrow? Okay? So scan the code, and if you can't scan the code, the link there is in the description, okay? The link is in the description. You're right, we're not finished. So remember, triple, we're going to keep going. If you're combined, so triple, you're still here. If you're combined, you're free to go now, and I wish you all the best tomorrow. I would love it if you could write us a review, okay? So if you could write us a review, that'd be awesome. If you check your email for how you got access to this lesson, you could write a review there, and it's just so nice to read how you guys find the lessons, if you find it helpful. It was free, right? Which is mad, so hopefully you're like, that was amazing anyway. But hope you're like, oh, Brooke's so good, she's such a great teacher. But it would just be nice to read how you find things. And it really helps us as a company to grow and just get help from many more people. Okay. If you're triple, we're going to take a quick break and we're going to come back. So for triple, I'm going to give you 5 minutes. So you're going to get to 20:09. You're going to get a quick break. And then we're going to go on to 8:30. Okay. So if you're triple, we've got more to go. You're so welcome, stated. If you're combined, good luck tomorrow. Make sure you eat some fish for your dinner. Make sure that you sleep well tonight. Fish helps brain power. If there was some part of the lesson today you thought, I maybe need to go back and do that again, it's all recorded. You can just go back, rewind it, go back to where you want to. Sadia, I love that. Thank you. So yeah, please, Chelsea, again, it can only get 5 centimeters in the air, so you're still safe. So yeah, I hope you guys enjoyed the lesson. Hope to see you in A-level physics in summer school or A-level physics next year. But again, it'd be lovely to read your reviews and all the best tomorrow. Yeah, all the best tomorrow. Megan, because it will pass through you to the ground. Specific latent heat is to do with a change in state. It's the energy to change state. It's you to calculate the energy to change state. Summer school is going to be like free lessons. Oh, I'm not sure if it's free actually. I think some of them might be free. It's not decided yet. But the summer school is just like lessons for you to get a head start for your A levels. So for example, I'm going to run a physics summer school for your 12s to get you started for your A levels. So it's just like a quick intro to what A level physics will be like. I heard Neil say you and him were together. What do you mean together? Like right now? I'm at home. Can I see your dog? He's dead to the world. He's hungry. Look, he's dying. Baba, you gonna come here? No, he's not moving. He's not moving. You could rewind it to earlier, he'll move, but yeah, he ain't moving right now. He's done. Yeah, all of summer school. Lord, no. Where'd that come from? No. German Shepherd. German Shepherd's not moving because he's hungry. Summer school is on our website. Summer school on our website. But again, All that information will be given to you. If you go to TikTok, again, if you follow me on TikTok, Brooke Does Physics, there's loads of extra content there for you guys, okay? Pick him up. Physio, he's massive. He's like 35 kilograms. That's not happening. Okay, so if you're doing triple, I shall see you in 3 minutes. Yeah, 3 minutes. Physio, feed him. Yes, a hill there will be. He's called Bubba Juk. Ali, why do I prefer physics? There are loads of jobs. There's so many jobs you can get for physics. Way more than biology and chemistry. Way more than biology and chemistry. So yeah, the free resource, just click the link and it'll ask you for your email so they can send it to you. So yeah, if you click the link, it's in the description. For the free resource, click the link in the description. A link will pop up where it asks for your email. Or it might just be that a lot of people are clicking on it right now. So maybe just give it like 5 minutes and then try clicking on it then. But yeah, click on then. And they'll send you an email. But just give them time to send it out. So you'll probably get it within the next like half an hour. Do you like the NFL? Yes, I do. Okay, guys. I'm going to quickly run to the loo for 2 minutes. Yes, 2 minutes. I'll see you in 2 minutes for triple. Awesome job today, guys. 2 minutes for triple. 2 minutes for triple. Okay, 2 minutes for triple. 2 minutos. Bye. Good luck tomorrow. Let me know after how it went. I'm back. Right, triple folks. Are you ready? Last 25 minutes, 20 minutes of some triple content for tomorrow. George, it's all aimed at AQA, but like Edexcel, OCR, sorry, it's all kind of the same stuff. Yeah. Oh, Daniel, better to write electron, but E-minus is also fine, but better to write electron. The way I disappeared, it appeared. Jason, if you haven't got the revision resources, it'll just, because they have to send the email out to everybody, give it half an hour. But yeah, you'll get them for tonight. Okay, let's go. It says, a student investigating the relationship between pressure and volume of a fixed mass of gas at a constant temperature. Explain why, when the volume of the gas decreases, the pressure increases, using ideas about gas particles. So the volume drops. So look, the volume is getting dropped. Why would the pressure increase? What we're saying. Cooper, you used the link for revision forces 2 days ago. What do you mean? Sure, it's only been live today. Okay, collisions, good job. So we know there's going to be more collisions. Is that enough? So a lot of us said more collisions. Do you think that's getting you the mark? You're missing something. Thank you, Imani. It's more frequent collisions. You have to say the word frequent, or you can say more collisions per second, either one. So if I make the volume smaller, there is less space, right? There's less space for the particles to move. I can't spell for. For the particles to move. If there's less space for the particles to move, we know what's going to happen is there's going to be more collisions per second, right? So what we said is every second there's going to be more collisions. And because pressure is equal to force divided by area, there's going to be an increase then in the force. There's going to be an increase in the pressure. Okay, again, because we said there's less space. So because there is less space, there's that more frequent collision. So please don't forget that word frequent. Okay. Right, next one. A student compresses the gas and they make it smaller. And we want to look at Boyle's law. How do we figure out these missing values? What do we do here? Hasnian, what's wrong? What would you? Yeah, Isabel, I agree. Hasnian is not nice. If you're rude again, Hasnian, you're going to be removed. We're positive vibes here. We've got a test tomorrow. What is Boyle's law? Everyone help. Yeah, Reese. It's what Reese wrote. Boyle's law is that equation in your formula sheet that says P times V, pressure times volume equals a constant. So you see that one on your formula sheet. Pressure times volume equals a constant. Okay. So what I need to do first then, pressure times volume is a constant. Yeah, nice, good. Nope. Pressure times volume is a constant in what says in your formula sheet. So what we're doing first. Who's Boyle? He's a scientist who figured it out. What is a constant? A constant means it's a fixed value or a set value. A fixed value or a set value. That I can't spell. Why can I not spell today? Set value. So it means the number doesn't change. Mohammed, good. So the first thing I want to do is we're going to figure out what is this constant. So I've got the volume, I've got the pressure. So I'm going to multiply them together to find out what is this constant. Yeah, Tilly, Hazel. Yeah, beautiful. So we're doing 200 times 50, which gives us 10,000. So it's going to give us 10,000 is our constant. Does everyone see that? So 10,000, yeah, that is our constant. That's our constant. So it's always the same number, set value, same number. So what I know now is 150 multiplied by something has to give me that constant, that fixed value. Yeah, this is triple science now, coffee. Yep, Tabby, good. So to get what that missing number is, we do the opposite of multiply, is that we divide both sides by 150. So if we divide by 150, what do we get? So what we're doing is we're going to do 10,000 divided by 150. And we're going to get that number then of 66.6 recurring. So is 66.6 going to get me marks on my test? You guys are all triple, so hopefully we know what the right answer is. It's going to be no, because the answer is 66.6 recurring. Yeah, Maka, beautiful, which is 66.66666. So remember what that means is because the number is above 5, you round up. So you can write 66.67, or you can write 66.7, or you could write 67 even, but you can't write 66.6. Okay. Right, next one then, I know that 100 times by something equals 10,000, equals that constant. So to find the something, I just divide both sides by 100. Yep, Joey, beautiful. And we're just going to get 100 again. So that missing number there is 100. Good. So just make sure we learn that this is on your formula sheet. It says pressure times a volume is a constant. It's a constant. Nice. Yeah, beautiful, guys. Easy. Okay, next one. This one is talking about decay. So it says, a radioactive isotope has a half-life of 6 hours and is used in medical treatments. A hospital receives 16 grams of the isotope. What is meant by half-life in the context of radioactive decay? So what is half-life? Evan, give me a second and I'll help out with that in a second. What is the half-life? Yeah, Harry. Yeah, you just have to rearrange the words. Half-life is the time taken Yeah, there's loads of ways to write it. Time taken for the activity to drop by half. Instead of writing activity, like other people wrote there, instead of writing activity, you could write time taken for the mass to drop by half. Instead of writing activity or instead of writing by mass, you could write the number of nuclei to drop by half. Yeah, so be Carol Dillon, you have to say not to decay, you have to say to drop by half, to decrease by half. Yeah, to drop by half. So half-life is time taken for the activity to drop by half, or for the mass to drop by half. Yeah, Jay, or the count rate to drop by half, or the number of nuclei to drop by half, Sienna. Yeah, good job. No, not radiation. The number of nuclei, the mass, or the activity to drop by half. Yeah, nice. Or count rate, Jay. Yeah, was good. How much of the isotope is after 18 hours? Nope, this is combined and higher triple. So I know the half-life is 6 hours. I'm starting with 16 grams. How much is left after 8 hours? Oh, was it 4 or 2? Good, right? Good. The answer is going to be 2 grams. Remember, the half-life, it told us the half-life there is 6 hours. So it tells us the time to drop by half is 6 hours. So over 6 hours, it's going to drop by half to 8 grams. But I want 18 hours. So again, another 6 hours, it's going to drop by half to 4 grams. But in total, that's only 12 hours that passed. So I need another 6 hours to get me down to 2 grams. And then in total, that's been my 18 hours. Yeah, Cooper White, I love this. Yeah, Aisha, you can do that way too. Yeah. Okay, if the isotope's activity was originally 400 becquerels, how do we calculate the activity after 12 hours? So we started with 400 becquerels. How much is left after 12 hours? Yeah, nice, beautiful guys. The answer is 100 becquerels because remember, we said half-life is the time it takes for the activity to drop by half or the mass to drop by half. So this question, we saw that the mass dropped by half, but this question, we're seeing the activity is going to drop by half. So we know the half-life is 6 hours. So after 6 hours, the activity is going to drop by half. But I want 12 hours. So again, after another 6 hours, it's going to drop by half. So that'd been a total time of 12 hours that passed. So I know I have 100 becquerels left. Yes, head, decay by half. Yeah. Nice, good. Okay, explain why isotopes with short half-lives are useful in medical tracers, but those with long half-lives are used in smoke detectors. So a medical tracer could be that you might inject someone with a radioactive isotope. So we inject them with it and it travels in their blood. And then wherever it gathers, we can figure out where the tumor might be or where the problem might be. Why do we want it to have a short half-life? Yeah, there's going to be less exposure to radiation. Why? Why do we want to have a short half-life? Remember, half-life is the time it takes to decay. Yeah, good, nice. A short half-life as we don't want it to remain in the body for a long time. So we don't want it to remain in the body for a long time, right? I don't want to put in the body for a long time. I don't want to put an isotope in my body that's got a half-life of 6 years, right? That means that 6 years later, I'm still going to have radiation in my body, right? I want to put something in my body that's maybe got a half-life of, I don't know, an hour, so that an hour it's all dropped by half. After 2 hours, it's dropped by half again. So I don't want to keep that radiation in my body for a long time. So I want to make sure it's got a short half-life so I'm not putting that ionization in my body for a long time. Yeah, less exposure to that radiation. Why, though, in smoke alarms do you want a long half-life? So why in smoke alarms do we want a long half-life? Saf, what? Why do we want a long half-life? Yeah, Stanley, right? We want them to last a long time. So you want them to last a long time. We don't want to replace them, right? So we don't, yeah, Al M, that's nice. We don't want to replace them. So we want them to last for a long time, right? We're trying to save money here. Yeah, nice. Why is gamma radiation used and not alpha? So when we put this isotope in our body, why do we want it to emit gamma radiation and not to emit those alpha particles? Yeah, beautiful. It's less ionizing. That's a key thing, right? It's less likely to cause me cancer. Why else is it important though? What else can gamma do that alpha won't be able to do? What else can gamma do that alpha can't do? So remember, what we're trying to do is trying to take pictures of the outside of the body to see where is the problem, to see where that radiation. Yes, lovely, nice, Ali. We know that the gamma radiation, so gamma can leave the body so that we can detect it. As It is the most penetrating. Right? So we can see where that cancer is. We can see where that tumor is. We can see where the problem inside the body is. But if it was alpha, it's just going to stay in the body and we'd never be able to see it because alpha can't even get through paper. So it's not going to get through our skin. Yeah, nice. Good. Okay, a factory uses a radioactive tracer to trace the thickness of paper in production. Explain why beta with a medium half-life is chosen instead of alpha or gamma. Why do we use beta? Why do we use beta to see the thickness of paper, but not alpha or gamma? Right, Elle, good job. Alpha can't get through paper. Right, so I'm never going to figure out how thick it is. Yeah, Bella, and gamma can get through lead even, right? So imagine I've got a single piece of paper. Let's say that paper's too thin, right? Do you know how you can buy paper from the shops and some of it's too thin and you can see your ink on the other side? So let's say I've got something here that's going to be emitting, here's my source, that's going to be emitting my beta particles, right? My fast moving electrons. So there's my beta particles. And here is my detector, right? There's my detector that is trying to detect those beta particles. If the paper is too thin, all of those beta particles are get through to my detector. So because my detector detects lots of beta radiation, I know that's too thin. So what I'm going to do is I'm going to make the paper thicker. So now I make the paper thicker. And now what happens is maybe only some of the beta gets through because the rest of them get stopped. So now I know my paper is the perfect size. But if my paper is too thick, none of the beta will get through it. And that's why my detector detects nothing and it knows my paper is too thick. But we couldn't do that with gamma because gamma radiation can get through the paper. Gamma radiation can get through thick paper. Gamma radiation can get through really, really thick paper. So I can never detect how thick the paper is getting. It's only the beta that can able to control how thick that piece of paper is. Okay. Okay, nuclear power stations. So what we got left, everyone can see, we're doing nuclear power stations and we are done. Okay, so nuclear power stations and we are done. So says uranium-235 is used as the fuel in nuclear power stations, okay, and not its isotope uranium-238. So I've written this all here so you can highlight it. So when uranium-238 absorbs a neutron, it just gets heavier, right? Nothing happens to it. So we always want to have the uranium-235. Can you pop in the chat, what is an isotope? Just make sure we're good. What's the difference between 235 and 238? 235 is what we use in our nuclear reactors because they are fissionable. They are unstable and it decays into smaller nuclei. Okay, what are yeah, good job. Isotopes have the same number of protons, but they have different numbers of neutrons, right? So that's why we've got 235 and 238. They have different numbers of neutrons. They have different mass numbers. Good job, guys. So again, we want to have uranium-235. We want to get rid of the uranium-238. As we only want to dig up from the ground uranium-235. We just half it. Half-life, just half the number. Every time you just half the number. Obradara. So what it says here is that we know that it's going to decay randomly. So make sure you know that it's a random process. It might never decay. It might all decay at once. And what's going to happen is when it decays, it always releases multiple neutrons. If you say one neutron, you'll not get the mark. So again, what happens is we have a neutron and it's going to get absorbed by that uranium-235. So there's my uranium-235. It absorbs the neutron. And then what happens is that large nucleus is going to break up into our lighter nuclei and releases at least 3 more neutrons. Don't say and a neutron because you're not going to get a mark. You have to say 3 more neutrons. Yeah, so Pam, for the free resource, remember, just a lot of people have asked for it right now, so it's just going to take people the time in the office to send it through to everyone. So yeah, give it in half an hour probably. So more neutrons and energy in the form of gamma radiation. Okay. So what we're saying here is the uranium-235 is in the fuel rods, right? I've got these things here called my fuel rods. So that's where my uranium-235 is. It's inside the fuel rods. And we've got these things here called our control rods. Your control rods, they do exactly that. They control the reaction. So what we can do is we can raise the control rods or we can lower the control rods. If I raise all of the control rods, if I pull them all out, what's going to happen is I'm going to have loads of those neutrons free to cause fission. But if I lower all my control rods, so if I push them all down, what's going to happen is that they absorb the neutrons so that they're no longer inside the reactor. And if we get rid of all these neutrons, so they're so no longer in the reactor, they're never going to collide with any more uranium. So we've completely stopped the reaction. So what your control rods do is they control the reaction because they can absorb the neutrons. Okay. Water we use as a coolant or a moderator. Okay. You might not have seen the word moderator before, but it could be like an applied question. So water is used as a coolant because it can absorb all of that energy, right? Absorb all that thermal energy. And one question I've seen before is, why do we use water as a coolant? What is a property of water that we use as a coolant? No, Aish, your answer is always the same, to absorb neutrons. What is a property of water that we'd use as a coolant? Bella, good. It's got a high. Daniel, good. It's got a high. Cooper White, good. It's got a high specific heat capacity. So what that means is it can absorb loads of energy before it changes temperature, right? So water is used as a coolant because all of this is going to produce a lot of heat. So what we can do is we can have loads of water here. So you can see that the coolant goes in, loads of water here because it's going to absorb all of that heat energy. And then what happens when it absorbs the heat energy? What does it turn into? So the water is going to absorb all the heat energy, and what's it going to turn into? Warrior, that's good. Why you're here now then. It's going to turn to vapor. Stanley, good. It's going to turn to steam. And what do we think we use the steam to do? What do we use the hot out to do? What is the steam going to end up doing? Think about what we learned earlier. The steam is going to do what? Yeah, this is AQA. You do need to know this. Yeah, the steam is going to turn a turbine. Good job, guys. Yes, it's going to turn a turbine. The turbine is going to do what? Yeah, it's going to spin a generator. Right? And then that's how we get electricity out of our nuclear reactor. Good, right? Yes, and yes, if you're AQA, yes, you need to know this, okay? If your teacher hasn't taught to you, maybe you just missed a day of school, maybe they forgot, but yes, please learn this, okay? So water can be used as the coolant or the moderator. It can be used as both. And one thing you might see is, see these neutrons we said earlier. So see these free neutrons that came out. What the problem is, they have loads of energy. They have loads of kinetic energy because they're moving really fast. So sometimes because they're moving too fast, we want to slow them down. So to slow them down, sometimes we have the water there because they'll collide with the water and then they get slowed down. And it just makes sure that then they can go on to collide with another uranium-235 nucleus. Good job. Okay, so key things here. Please make sure that you have learned the uranium-235 is our fuel. What's the other fuel? It's going to come on the other slide. Uranium-235 is the fuel. The control rods, because they absorb the neutrons. They absorb neutrons. Water is the coolant because it's got a high specific heat capacity. And sometimes these neutrons are moving too fast, so we need to slow them down. Good. And the other one we can use is plutonium. So good, that comes to this question now. So last slide today, guys. You have done so well. We got this. What is nuclear fission? What would you write for question 1 on your test? What is nuclear fission? What is nuclear fission? What would you write in your test? Lily, no, you forgot about your turbine. You do need a turbine in there. I've seen a 4-marker before asking you about what happens to that water from the nuclear reactor, and you did need to mention turbine. And moderator is just something like water. It just wants to slow those neutrons down, Eris. But that's a bit extra. That moderator bit's a bit extra. Just to make sure in case you get an applied question. Mac attack. Nuclear fusion. But I asked about nuclear fission. So if anyone wants to know about nuclear fusion, what Mac attack wrote is perfect. But I didn't ask about that. I asked about nuclear fission. Oh, good. Missed. I like yours. Yep, I'm happy with yours. Okay, better if you said that nuclear fission is when a neutron is absorbed by a large nucleus that splits into lighter or smaller nuclei and you can say 2, but it's better to say 3, and 3 more neutrons, and energy is released. Nice. Right, plutonium, we said, was another fuel that can be used. For fission to happen, the nucleus must absorb a particle. What type of particle must be absorbed? I kind of just said it in that previous question. So what we're saying? What type of particle gets absorbed? We kind of just answered in the last question. Yeah, it has to be a neutron, right? This was a past paper question. A neutron is what gets absorbed. Yeah, easy guys. It's a neutron that gets absorbed. Nice. Fusion is another process to release energy. It must occur at very high temperatures. Why? So fusion, remember, is when we have 2 light nuclei and we're trying to join them together. We're trying to join them together. Why do we need really high temperatures? Right? Yeah, nice. We need high temperatures to increase their kinetic energy. We need high temperatures to give them lots of energy, to give them, yeah, Ola, good, to give them lots of energy, lots of kinetic energy. Why do they need lots of kinetic energy, though, was the question. And it's what Ola wrote there and what a few people wrote there now. Good job. Because remember, nucleuses, they only have protons and neutrons inside them. Protons are positively charged and neutrons have 0 charge. Protons are positive charged and neutrons have 0 charge. So what I've got is 2 positively charged things and I'm trying to get them to move together. I know that they want to repel each other. So I had to put really high temperatures to get them close enough so that they're actually going to join with each other rather than repel each other. Yeah, good. So high temperatures to give lots of kinetic energy to overcome, that's lovely Bella, that's lovely Warrior, to overcome that electrostatic, so nice if you know that word, electrostatic from paper 2, electrostatic force of repulsion between the 2 positively charged nuclei. Nuclei is just a better way of saying like nucleuses, basically. You don't have to say electrostatic. Key things I want here is that you want to say we want to make sure you say repulsion and say that the nucleuses are positively charged. Yeah. Yeah, 1 and 2 is fission and then blue is the fusion. Fusion is what happens in the sun. That's where it's really high temperatures. Okay, last question today. What is an advantage of fusion over fission? What is an advantage of fusion over fission? Sun is epic. No nuclear waste. Good job. There is no radioactive nuclear waste. So what that means is disposal costs less money. Nice, Bella, right? You can't just say it gives more energy. You can't just say it's more energy. It's more energy per kilogram of fuel. So if you had the same amount of fuel, we're going to get more energy over fusion. You can't just say one gives you more energy. You have to say per kilogram of fuel. Yvonne, good job. We know that the reactants, or RE, I can't spell reactants, the fuel is easy to get. Does anyone know how do we get the fuel? How do we get the fuel in fusion? How do we get the fuel for fusion? Oh, JT, there is no link yet, but if you follow us on TikTok at Brooke Does Physics, I post loads of reminders about it and loads of ways to get onto then, or follow us on Instagram at Brooke Does Physics, Brooke Does GCSE Physics, or Brooke Does Physics. Yeah, good job. It comes from hydrogen. So where do you think we get the hydrogen from? Where do we get hydrogen from easily in the earth? Yeah, water. Good job. Yeah, nice. We just get the water. So we just get hydrogen from the water. So the fuel is just readily available. So the fuel is really easy to get, or it's really, really readily available. Or for fission, we have to dig up the plutonium or dig up the uranium from the ground. Look at you guys writing electrolysis in your chemistry knowledge. Yeah, nice. Guys, we are done. Okay. Hopefully you guys have had some chemistry lessons with LaJoy, some biology lessons from Laura. There's maths lessons going on. There's English lessons going on. Bella, you're tired. Remember, free resource. So somebody said you hadn't got it yet. You will get it. It's just because a lot of people were maybe applying for it one time. It's a lot of emails to send out, and sometimes it takes a lot of time for like if 3,000 people applied. takes a few people to go out. Zanera, what's wrong? Remember, if there's a part you didn't get, that's the best thing about it being recorded, right? You just can go back and watch it anytime you want, right? You've got, it's 8:39. I would recommend you spend now, go talk to your family, go get some food, go get a rest, go walk your dog. Spend an hour doing your own thing right now to 9:30. And then from 10:30, 9:30 till like 11 o'clock, just revise the stuff from today that you didn't get or watch the lesson again. Go to bed at 11 and get a good night's sleep. Okay. Try to get minimum 6 hours, better if you can get 7 or 8. Okay. And wake up tomorrow, make sure you get a good feed and you're feeling energized and you're ready to smash that exam, right? Minty, I'm so glad. And it would be lovely if you could leave us a review so I can read them, which would be lovely. And please let us know tomorrow if you just, I'm going to post a TikTok tomorrow asking how it went. It'd be lovely if you could reply, let me know how things went. Yeah. So hopefully this was a quick refresher for you guys and feeling like, okay, I forgot about that from school. I got it there today. So again, some of you might find the first bit too easy, the last bit too hard, but it was just trying to go through an overview of stuff that you might have missed from school or you might have forgot from school. Just that quick recap, that quick cram of stuff for tomorrow. Can't wait for a lot of maths. So good luck. You will smash it, I'm sure, and then let us know after. Yeah, 2.1k likes. We made it. Harvey, yes, someone asked about that. So thank you, Harvey, for answering that. Harvey, I'm just going to pin your message because I can't remember who asked me that, but that's perfect. Guys, have a lovely day. Hopefully I'll see you for equation, or not equation. Hopefully I'll see you for paper 2 cram. Sophia, that was asking to find out what the uncertainty is, and you do half of the range. Uncertainty is half the range. I made a few TikToks on it recently. So if you go to Brooke Does GCSE Physics, there's quite a few there talking about half of the range for uncertainty. Yeah. A big advantage over fission over fusion right now is that it's easy to do on Earth. Fusion right now, we haven't really solved. We can do it on Earth, but we're not getting out a lot of energy because it costs so much money to get those high temperatures to get the nucleuses close enough together to join. Yeah. Yeah, when it ends, you can watch it again. Yes, when I end the lesson now, you have this link forever. You can just go back and watch it whenever you need it. Yeah. So this, guys, this is for you guys whenever you need it. So tomorrow morning, if you're like, oh, I need to watch that 10 minutes again on nuclear reactors, you can watch it tomorrow morning. Yeah. Yeah. I've got loads of conversions, Farah, on the TikTok page. If you go to TikTok, there's loads of conversions there. Yeah, loads of conversions there. And again, loads of required practicals on that TikTok page, right? But I don't want to kill you and I don't want to overwhelm you now. 3 hours is intense revision. So please go eat or go walk your dog or say hello to your family or do something and then go back and revise again, right? Take a break right now and then you can go back if you need to. Hopefully you don't need to, but just take a little break right now, okay? Riley, I don't know yet. I'm not going to lie. Space, Bill, is for paper 2. Yeah, paper 2 for AQA. Right, guys. Adios. Have a lovely day. Good luck. Bye. Bye.